Good morning and good evening, everyone. I'm Jinfeng Zhang, a researcher from Recon AIP. Today, I'm going to host the fourth TrustML Young Scientist Seminar. Before that, allow me to briefly introduce Recon AIP to our valuable guests. The full name of Recon AIP is the Recon Center for Advanced Intelligence Project. AIP was founded in 2016 as the Research Center for the Max AIP project. AIP Center conducts Japan's leading AI research, which is headed by Professor Sugiyama. AIP aims to enhance the AI's fundamental technology and its real-world application. AIP encourages the collaboration with various researchers and engineers in related fields. We would be grateful if our guests could visit us in our Nihonbashi office in Tokyo in near future. Next, I'm going to introduce our valuable guest, Jonas Gaping. Jonas received his PhD degree in 2021 from University of Siegen, Germany. He now is a postdoctoral researcher at the University of Maryland, College Park, United States. His research includes optimization in machine learning, the implication of the optimization in machine learning for privacy and security applications. Let's hugely welcome Jonas to give his talks, attacks on privacy in federated learning scenarios. Hi, Jonas. Can you share a screen right now?
Yep, thank you. All right, so this talk will be attacks on privacy in federated learning. And what we'll talk about first is what is federated learning. Then we will talk about gradient inversion attacks, which really are the core of the question of privacy in federated learning. And we'll discuss these attacks in the threat model of honest but curious. And we'll talk about this later, what this means. And we'll also discuss malicious threat models. We'll then discuss defenses, and this will be the talk. And before I start, I'd like to thank a number of co-authors. And especially, I'd like to mention Liam Fowle and Yuxin Wen, with whom I've worked on some of the projects in the last half year, which you'll see later on. Also, feel free to please always interrupt me if you have questions. And yeah, let's just keep this very informal. And if you have any questions, always interrupt me and just ask them. So let's start. Our first question is, what is federated learning? And in a nutshell, federated learning, for example, works on your smartphone in the following way. So there's some machine learning model that someone, for example, the company that owns your smartphone, or that maybe not owns, but for example, Google wants to train a next word prediction on your smartphone. So what they would do is they send the state of this model, of this prediction model, to your devices in blue, and not only to your device, but to a number of devices all over the country. And then on your phone, you write some text. This is port A here. And this generates an update to the model, which you see in the green square here. And then we can collect these updates from all these devices in part B and aggregate all these devices in the lower right corner, and then use all these aggregated updates together to improve the model in part C. And this can then be iterated several times to train a model for next word prediction on a large number of devices. And this is not just a concept, this has actually happened, for example, in the US for Gboard predictions, which is the Android phone app, basically. A bit more formally, we can think of two ways to train a machine learning model. The first way is centralized training, where we first collect all the data from all the users, and then we train our model normally by minimizing causality loss, for example, here for classification or some other task, for example, by stochastic gradient descent, and where the entire training of the model happens on the server. In contrast, federated learning splits this task up between the server and the user. the users here own their own local data, and they do not send their data to the server, but the users keep their local data and compute, for example, a gradient of the model based on their local data and send only the gradient to the server. The server then aggregates these gradients from multiple users and takes an update to improve the model. And then in the next step, the server will send this update out again, and this process will repeat. And what's interesting about this is that here, the server can train a model without ever seeing the actual user data. And there's some idea about this that because this is just gradients and it's not the full data, that this is more secure and that these gradients only contain information that's pertinent to the task. And this is just FedSGD, which is basically the simplest federated learning algorithm, but others exist as well. One I want to highlight that's also very popular is federated averaging. In federated averaging, the same task happens, but you can think that the user now does several local update steps. So each user separately does, for example, several steps of gradient descent to improve their model, and then sends their updated model back to the server. However, you can think that this is also sending back gradients in a way, because the user just sends back gradients to the server that have been aggregated in time, basically, over these multiple local steps. There are also a large number of other federated learning algorithms, which we'll not focus on in this talk, though. So this is the basic concept. And is this private? There's been a lot of, like, if you start Googling this or look at some of this, a lot of introduction material, it's very easy to find people that say, okay, this is very private and this ensures data privacy and security. The model updates are ephemeral, user data is basically safe. However, this is not always so clear. And the linchpin of this is actually the question, how easy is it to invert the update? If a user, for example, has this dog image, sends it to a network, computes the gradient, sends the gradient to the server, a very basic question is, how easy is it to invert this gradient and retrieve the user data from the image? And in all applications where this is actually easy, federated learning doesn't provide any privacy because the server could just as well recover the user data from the gradient. And this has all been found out. So it's a very important question for federated learning to figure out which applications are private and which ones aren't. So how could these attacks happen, these gradient inversion attacks? Let's first look at a simple example. In the simplest example, we have a fully connected layer. And it actually turns out that you can always recover the input to a fully connected layer from the gradients of its weights and bias. And we can actually do the computation because it's relatively simple. So if we have this linear layer, which computes, for example, here wx plus b, and its output is y, and we have some loss L of y, then by the chain rule, the gradient of the loss with respect to the weights w is the gradient of the loss with respect to yi times the input x. In the same way, the gradient with respect to the bias is the gradient with respect to the loss. It's the gradient of the loss with respect to the output, yi. So here, yi, each I here is a row in the weight matrix, and each bi is single bias. However, you might see here already is that actually the term of the derivative of the loss with respect to the output appears twice, namely in the weight gradient and in the bias, which means that we can actually recover the input to this linear layer by just dividing the weight gradient by the bias gradient. And this can recover the input to a linear layer if there's only a single data point. And we'll call this an analytic attack, and we'll discuss this later. However, this only works really for a linear layer. And of course, most models are more complicated than this. For convolutional filters, for example, you might think that an attack is harder, because each gradient for a convolution is just a 3x3. There's no spatial structure. And for example, for ImageNet, a single image already has 150,000 values in pixels. But the gradients, for example, in the first layer, there are only about 2,000 gradient entries in the first convolutional filters. So this seems very hard to invert from this back of the envelope calculation. However, what we'll look into the next step is how this can be solved by optimization. And so before we go into this part though, we will discuss a few ground rules for our attack. And in our first part, these ground rules will be an honest but curious server. And this notion of an honest but curious server is defined, for example, you always see the references down here. An honest but curious server is defined by a server that's honestly training a model of federated learning, where honest here means that the server is following the federated learning procedure to the letter as described, but the server can store and separately process user information because the server is also curious. So the server does the protocol normally and makes no malicious changes, but secretly the server records the user data and tries to invert it. So this is our first threat model. And the server does not do anything else. It doesn't send malicious architectures, fake parameters, or modify the algorithm. Right? The server is very honest here. So the best way to formalize the problem here is to formalize an optimization problem. The server receives some gradient g theta from the user. And now the task for the server is to recover the input data x from the gradient g theta. And because the server knows the architecture, because both parties know the architecture of the model here, the server can actually just optimize this nonlinear loss term here. And there's been some work on this. And for example, there's some work on this with an LBFGS solver. But in theory, you could use any iterative optimization algorithm for this. With an LBFGS solver, it doesn't scale very well. So you can use Atom, for example. And the Euclidean objective can sometimes be a bit hard to optimize. So you can also optimize this with a cosine distance. And then the question is, does it work? Which is probably what you're most interested in. And actually, it does work surprisingly well. So here's a ResNet 152, which is a relatively large convolutional neural network. And here we see that the attack can often recover a lot of image data. And I'm going to scroll through a few non-cherry-picked examples. And here you see the bird kind of works. This gecko works twice. Snake, another bird. This black swan doesn't work. This crab works, does work. So these attacks work surprisingly often. And some images actually are easier than others, which means that actually the privacy is very non-uniform. And it's hard to say beforehand if an image will be easy to recover or hard to recover. And furthermore, what's important to see here is that these are just visual representations of an actual attack. There's actually much more information leaked. For example, if we go back to this bird, here we can't really see the bird, but there are lots of features in this image. So for example, we see a lot of water features here, and we see that this bird has brown feathers, even if we don't recover the bird. So there are some features below the image level that are also leaked here. And this is just one variant of the attack, and there are strong attacks being proposed continuously. For example, this one from last year's CFPR. So these are gradient inversion attacks by optimization. However, these attacks are also somewhat fundamentally limited, because what I've shown you here is always just the recovery from a single data point, which means that there exists a user somewhere who owns only a single image, and the user sends an update based only on this single image. And these attacks are actually harder the more data each user owns. So if the user has 10 images, the attack will not be this good. And if they have 20 or 30 images, the attack in this way is almost impossible. And this gave rise to some belief that these models could be secured by something that's called secure aggregation, which means that the updates from multiple users are pooled together so that the server can only ever see, let's say, an update with a batch size of 1,000, which is far away from these attacks, so which makes these very safe. In the next part of this talk, so we'll discuss how secure aggregation itself can be broken and how other attacks could breach this threat model. But yeah, by the way, this also works not only for convolutional networks, this also works very well for modern networks, for example, like vision transformers. Here's an attack from this paper on a vision transformer. Also for a single image though. So let's go back to threat models. An important part of the last group of attacks was that these were all honest but curious attacks, which means that we had all these restrictions on what's an honest server, and the server is really only honest but also curious. But does this actually make sense in practice? And this is actually a very hard question to answer, because there are questions surrounding this, for example, are who chooses the model architecture for a practical system? Who has control over the server? And how much code can be executed in user devices? And all these questions are very application specific and very example specific. For example, some companies might do this another way and some companies another way. But these threat models actually have a massive impact on the actual privacy guarantees or privacy options that these algorithms have. Because really, this is about how much should the user trust the central party. And if the user trusts the central party less, and the central party is something else than honest but curious, then actually more attacks are possible. However, the attacks are also somewhat restricted because, for example, there are several current hardware features that make some attacks harder than others. One, for example, is sandboxing, which also has been recently implemented, for example, in Android as secure compute, which means that applications can be sandboxed easily. This means that, for example, if you were to write a federated learning application, then you could only interface with the federated learning interface on your Android device. You couldn't just halfway through your code, for example, write, oh no, I'm going to upload all my data to my server. Like you couldn't do an HTTP request in the middle of the program, for example. This could be solved by hardware sandboxing. Another thing that can be solved is aggregation. So you can aggregate the data from multiple users. So even if one user has just a few data points, then that user still can be aggregated with other users so that the actual batch size is very large. Another thing though is that users currently have no control really over the internal decisions. So if someone has a federated learning app on your device, you don't really know what model they're using, and you don't really know what parameters are loaded to the model, and the parameters are just floating point numbers anyway, which are hard to check. So there's really no control over this part of the pipeline. So one possible malicious threat model that we're interested in is malicious models. And what I mean here is, so the server, let's assume the server can choose the architecture. What would be the minimal change to a single model architecture that a server could make that could breach user privacy, which is discussed in this paper that I'm linking below here. And actually it turns out that a single linear layer early in the model is enough. And I'm going to talk in a bit about how this works. So how this works is there'll be a linear layer inserted early in the model, for example, at the beginning of the model, which we call an input module. And what this linear layer does is that it has a bunch of a width. And every row in this linear layer computes the same function of the data. For example, just an average over the entire data. And then this linear layer is followed by a ReLU activation. But this ReLU is modulated by the bias of this linear layer. So we have all these rows in the linear layer, and they compute the same function. But actually, we can choose the bias for each of these rows differently. And what this does is that, for example, the first row will activate for all images because the bias will be set very low, and everything will go through this layer. Then the next layer, next row in this layer will be a bias a bit higher, so most of the images go through this layer. And all the way to the very bottom, the last layer has a very high bias, so almost no data passes through this layer. And what this does is it imprints a structure on the data, where now every gradient of this layer will be a sum over all the data with this average value. For example, let's say that the 10th row in this layer will be all the data that has an average value less than 0.5. And then there's the next row, which has all the data with an average value less than 0.6. And you might see where this is going, because now that we have this structure, it can actually subtract all the data with a bias less than 0.6 from all the data with a bias less than 0.5, and recover exactly the data with a bias between 0.5 and 0.6. So what this means is that now we actually can separate the data into smaller parts. And if there's just one data point between 0.5 and 0.6, then we catch this data point and we can reconstruct it directly. And so this is how this attack is constructed and how it imprints data from the user directly into the gradient. And before I just showed you examples for like one or two images, here is now actually a large batch of 64 images. And here's the recovery. And with this linear layer trick, we can actually recover a frighteningly large amount of user data from this layer. Here, actually, most of the images are recovered. And we could make this layer even wider and recover even more data. So how wide does this layer actually have to be to recover some data? It turns out the minimal width that's necessary is just a width of 2. So we'll just have 2 bins in our structure here. We'll use the first row of the linear layer to measure all the data that the user has, for example, with an average less than 0.8 in this figure here. And then we use the second bin to measure all the data that the user has with an average of 0.8.1, for example. And we'll make a very small increment here, and then we can subtract both components and recover user data directly. And just using this small linear layer, we can recover data from an arbitrarily large batch. For example, here's an example for a batch size of 32,768. And we can reconstruct this chimpanzee image almost perfectly from this super large batch with just a few subtractions and a division. So these modified models are immediately very unsafe. And just basically any party that can smuggle this layer into a neural network can immediately recover private data from users, even if previous attacks failed. Another way to look at this attack also is that there might be applications where these linear layers occur very naturally early in the network. And for these applications, you wouldn't even have to change the model. There would be a linear layer occurring naturally. But what if the model architecture cannot be changed? So our previous attack was malicious models, where we changed the architecture. What if the architecture is fixed? Then actually we can still find malicious attacks, because it turns out that the update that the server sends to all users can be maliciously chosen as well. And in this third model of malicious parameters, there are a bunch of interesting considerations. Compared to the previous model, this third model requires no access to the model architecture. And this makes sense, for example, because in applications, the model architecture might be compiled and then sent to all smartphones. And for an attacker, this can be hard to change the model architecture because it's compiled into some device format and fixed on the device. Another thing is that for the malicious model, the attack has to be deployed when the model architecture is designed. However, an attack with malicious parameters can be deployed at any time. Every time the server sends an update to a user, which it does multiple times to many users, the server could just as well send a malicious update. And if you do not trust the server to send an honest update, there's immediately the risk of an insecure update that breaches privacy. And these attacks are interestingly also very ephemeral, because what this means here is that the server can send a malicious update once at 2 o'clock in the morning, and then just follow this up with a benign update all other times of the day. And the update can happen, the attack can happen, and immediately afterwards, the malicious update is overwritten by a benign update. And it's very hard to figure out in hindsight that this attack has actually happened. So how would the server choose malicious parameters? And an interesting consideration here is that user data is safe because of aggregation, which means that the user has a lot of data and all of it contributes to the gradient update that's sent to the server. And so what this means is that what the attacker has to do is they have to choose the parameters in a way that only one of the data points from the user is activated. And a very example of this is just a class attack. And what this means is that if we have a classification task, and let's say the user has 1,000 images, but each image for the user has a different class. What we can then do as the attacker is that the attacker can send a malicious parameter update where all the other classes are zeroed out. And just this one class remains that the attacker wants to target. And then the attacker sends this update to the user and gets back an update. And the update that the user sends back to the server now contains the gradient of only a single data point. And all the other gradients are very small. So this attack basically fishes out user data from a very large batch by making these separations. Of course, the simple class trick of just disabling all the other classes only works if the user has just one image for each class, which is maybe a bit unrealistic. So let's look into two other scenarios where this attack also works. So the first one is cross-device federated learning. Cross-device is a setting that's common in mobile devices where you think you'd have many users, for example, all smartphone users in the United States, and no users usually query twice, and users aren't identifiable by the server. In this setting, though, what the server, if they are malicious, what they can do is they can use some group of users to estimate the distribution of a single feature in the last linear layer. And then the server can move the decision boundary of this feature so that almost all the data is excluded. And then only a single data point dominates the aggregation and can be recovered. For example, here, we see that in the top part, there's a normal attack, as I described in the previous section. And for a batch size of 32 here, the attack completely fails and just recovers 32 images of garbage, basically. However, the malicious update in the lower part actually fishes out this one shark image very precisely because it focuses just on this one image and suppresses the gradients of all other images. And this way, the attack can breach arbitrary aggregation sizes and break secure aggregation. That was cross-device. And this only works if we have a large group of users from which we can estimate statistics. Another federated learning scenario is cross-silo, for example, in a hospital, where we think we'd have very few users, for example, just a group of hospitals, and each user has a lot of data, but each user is uniquely identifiable and can be queried several times for the data. And in this scenario, what the attacker could do is that the attacker could actually just ask a single user several times. And every time the server asks the user, they figure out what their user's average feature value is, and then move the attack so this feature value is excluded by a half, which means that the attacker can actually make this sort of binary tree and target down a single data point from a user. And it turns out this is a binary tree, and actually to find a single leaf of this binary tree takes just about log many queries, which we also verify here empirically. And this is really not a lot of queries to this user. Like, for example, even if the user has 10,000 data points from a single class, it would only take 13 queries, so 13 rounds of this update for a server to uncover a single data point from this user. And this attack, here are some examples where this attack works for batches 256 and recovers actually so much data that we had to censor a bit of the image data here because it recovers the data so well here. So those were a bunch of malicious parameter models. And what I also want to talk about is what about language data, actually. And it turns out for language data, for example, transformer models in language, we can do some of these similar tricks. So again, we're looking at malicious parameters. And we want to modify the parameters of this transformer model to extract as much user data as possible. We'll have to shorten this a bit, because basically we can also do attacks with malicious parameters against language models and recover a lot of text from language models. And this works for BERT models, GPT models, for a range of models, and can actually recover a lot of text from these device updates. Potentially, this can recover several thousand tokens, which is almost a full Wikipedia article. And you can look into this paper that we have about this, and you'll see that we have almost a full Wikipedia article of text in the appendix, which such an attack could recover. So these are malicious parameter attacks, and there are some other variants of these attacks that I would just want to highlight. For example, there are also attacks that can send different models to each user to identify these users from Peshkini et al. And there are also attacks that actually use metadata in the updates to reconstruct users. For example, metadata like what kind of TensorFlow version the user has, or how old their device is, what's the device name. These attacks can work in addition to all other previous attacks. And there's some different variants of all this. So what we really want to highlight here is that these systems are actually very complicated. And many components in these systems can have very unexpected security risks. There are some defenses, and I just want to very briefly highlight two ones. The first one I'm going to call sophisticated defenses, which you've probably seen some papers about. It's like someone rakes an attack, and there's a very sophisticated defense that tries to defend against exactly that attack. This is often hard to do right and hard to trust, because some of these defenses also only work against very specific attacks. For example, you could look at this transformer attack that I just showed you and figure out which parameters it changes and check whether these parameters are changed. This would defend against that specific instance of that kind of attack. But this is very hard to do in general, and very hard to trust that this will be a very secure principle of defense in general. What's a much stronger defense in general is provable local differential privacy, which does protect privacy, provably if enough differential privacy is added locally. But this also reduces model performance and impacts model fairness. Okay. So one thing I also want to say is we have some code for this. So you can actually replicate all the attacks I showed you from our open source implementation on GitHub, which you can just install from pip. And this is just a PyTorch package that we made to reproduce all these attacks in all these scenarios. This might be of interest to you. All right, some conclusions, and then maybe we'll look into a discussion. So what we really want to highlight is that federated learning by itself is not a privacy mechanism. Federated learning can be made safe, for example, with differential privacy and with a lot of care, but just bare bones federated learning by itself is not a privacy mechanism. And this is because these modern machine learning applications leave a lot of room for many attacks. And I just showed a few attacks, and especially if we do not trust the server, then there are a lot of attacks that are possible. So any application that involves federated learning has to be very carefully designed to rule out all these possible attacks. We still think that federated learning is a very promising paradigm for the future for decentralized training, but there has to be a lot of care taken to make sure that federated learning is safe. Okay, and with this hiccup near the end, I guess I'll end my presentation, and please let me know if you have any questions.
Thank you very much for your great talk. I basically have two questions in the chat box. Can you able to see it?
I think I can't see the chat box.
Yeah, I forget.
Maybe because I cut out there.
Yeah, reconnect. Yeah. I have two questions basically. The first question is, we see that privacy leakage what the differences between the traditional kind of thing, differential privacy and the privacy attacks you propose, gradient inversion attack?
Yeah, I mean, basically, this was my last slide. We think that classical differential privacy is still a crucial mechanism to defend against these attacks. And a sufficient amount of classical differential privacy will defend against all these attacks.
Yeah.
On the other hand, though, for example, a lot of these attacks are very robust to small amounts of noise. Just because these are nonlinear optimization problems, and they, for example, if we add just some Gaussian noise to these gradients, which would be like very slight empirical, you can think of this as very slight empirical differential privacy, these attacks still work very well on these low levels of privacy, low levels of noise, basically, where we just have very small privacy parameters. But if we actually do the full computation and figure out how much noise we really have to add to make these models private, then these attacks do work against them. A lot of our work here is basically just getting people to use differential privacy more.
Okay.
Because they should be using this for all these applications, otherwise these are not safe.
Okay.
And these attacks are possible. There's some interest in, for example, in some of these bigger companies to not use differential privacy because it impacts their model performance. So they're more interested in maybe not doing it, but we think that's not a good idea in general, and just cannot be safe in general.
Right.
Yeah.
Right. Okay. My second question is there any metric that measure the degree of privacy leakage?
Yeah, this is actually a hard question to really find a good metric, because at some point this is almost a binary choice, which is either there is enough data leaked that you can identify the image, or it isn't. And a lot of these papers, for example, look at Pearson R scores, or look at these, for example, for images, look at these image metrics. But these just give a very incomplete picture of the whole thing. Because it doesn't really matter if, for example, we had these images from this, we saw a lot of images, for example, these sharks. It doesn't really matter if the shark is recovered through like a Pearson R of 20 or 30, which both of these are basically good shark reconstructions. But there's a point where it's like the Pearson R is maybe just like 12 or 13, where you cannot distinguish this shark from other sharks.
Yeah.
But at some point, at some point it shifts, and people have tried. So one metric to measure this is image identifiability precision, which has been discussed in unit all see-through gradients, one of the papers we reference. They measure this in a bit of an incomplete way by checking if the image that's recovered is closest to any other images in the training set, which basically is like doing a membership inference test on this reconstruction.
I see.
And this is a bit incomplete because the image might be close to real data by accident and still not look very recoverable. But often this gives us good information that at least this image is closer to the real data point than it is to any other data points in the training set. So this is one measure that goes around this, and it's actually binary. And either the image is the closest, and then we count this as a privacy breach, or the image is not the closest to any in the training set, and then we count this as a failure. So this is one metric to measure this.
Okay. I got it. So I also have a question. For example, for kind of like the hospital things, they use the image. They also use the tabular data, like some things. What do you think of the gradient inversions impact on the tabular data? On the hospital data, kind of like this.
Yeah, I mean, in principle, I do think that these sort of attacks can work in any scenario. And for example, especially in tabular data, it's a bit of a question on how which machine learning model is used there. And for example, there are some scenarios I've seen where there's a lot happening on the device. For example, there are lots of pre-computed features where actually each hospital recomputes these features and just sends some of these features to the server. And so the actual model that's trained collaboratively is very small. And this makes these things comparatively safer. Then also, for example, some of these more modern things where maybe a whole machine learning model is trained. That's because really this is also about size, right? The larger these models are, the more data they leak. But on the other hand, it very much depends on the model architecture and on these settings. So, and some of these attacks can probably be, so one thing, for example, is this the attack that we show on linear layers. This attack can probably be used on a tabulated dataset as well, where there is some linear computation of the input features.
I see.
Yeah, I haven't seen a lot of people doing this, but conceptually, this seems like a possibility as well. To do this for tabular data.
I see. Okay. Right now I have no questions, but anyway, thank you for your answering my questions. It's quite inspiring. Is there any question from our audience? Please feel free to ask here. And now it seems no. Anyway, let's sincerely thanks Jonas to give us his wonderful talks on his research. Thank you very much. When the situation is lifted in the future, we sincerely hope you can visit us in our Nihonbashi office in the near future. Yeah. Hopefully this pandemic will end this very soon.
Yeah, we'll keep our fingers crossed. Yeah,
yes,
thank you so much for having me, and have a great day.
Have a great day. Bye-bye. Yeah.
Bye.
All right. Hi, Dan. I think Danica is here. Danica. Yes. Can you hear me? May I introduce you first? Then you can get started your talk. Great.
Of course.
Okay. Danica Sutherland is an assistant professor in computer science at the University of British Columbia, Vancouver, and holds a Canada Safer AI chair at AMI. She received her PhD in 2016 from CMU and was previously research faculty at TTI Chicago and a postdoc at UCL. Her research broadly focuses on representation learning, particularly in the form of learning deep kernels, especially on problems involving understanding the differences between probability distributions. Let's sincerely welcome our guest, Danica, to give her talk, data set the scene, learning kernels for efficient and fair two-sample test.
Thanks.
All right.
Okay. So,
good.
Oh, sorry. Are you? Okay. Yeah. So feel free to interrupt with questions at any time. I have the chat open, or just unmute yourself. Okay. So I'm going to talk about two-sample testing, and specifically, well, a couple of variations on two-sample testing based on a few different papers. One of these co-authors is I see here in the audience, and with a whole bunch of people on these couple of projects. Okay, so in kind of the textbook machine learning setting, when we teach our undergrad classes or whatever, what we say is we have a bunch of IID samples from some distribution P. We expect that the training error should be roughly equal to the test error on P. And so minimizing the training error will give us a model that will be good if we see more samples from P, right? But in reality, I mean, first of all, we usually don't actually have IID samples from some well-defined distribution, right? But forgetting about that for a minute, we also don't always know that the training error may not always be a good approximation of the test error, because we're using these big neural network classes. and we still don't really understand quite what's going on there. Also, the thing that we're going to focus on today is that when we actually take our model and we go try to use our model in the world, the distribution of data that we see in the real world might be different from the distribution P. We're hoping that it's kind of similar, but it's probably not the same. It's probably changing over time, right? And so the problem we're going to focus on in this talk today is detecting whether P is different from Q. So one question we might really want to ask is, given some samples from P and some samples from Q, and not making any like super strong assumptions beyond that, it would be nice if we could understand, okay, how is this distribution P different from some other distribution Q, right? How is our training data different from our test data? This is a hard question. So I'm not going to try to answer that today, really. Something that's maybe enough would be saying, okay, is P close enough to Q for the purposes of our model? This is a question people have also studied. It's also not what I'm going to try to tackle today. What I am going to try to tackle today is a very specific question, which is, are P and Q exactly the same? This is a limiting question, but it's a question that I think we can make pretty good progress on using the methods we'll see today. And it has something kind of vaguely to do with the two questions above that, which are probably what we really care about. So the formal framework that we're going to use, so we have samples from two unknown distributions, and we want to ask, is P equals Q? This comes up not only in this kind of data set drift, as I mentioned, but in all kinds of places, right? Here are a bunch of examples. These are all various kind of real world or real world-ish examples of using these two sample testing techniques to answer these kinds of scientific questions that you might care about. Another one I'll point out is that independence testing is kind of roughly equivalent to two sample testing. So that's also good to know. Okay, so the specific technique or the specific like approach we're gonna take is null hypothesis testing. And specifically, we're gonna say, okay, the null hypothesis is that they're the same. The alternative hypothesis is that they're different. And if we have some test statistic T hat, which is big enough, then we're gonna be confident that the two distributions P and Q are actually different, based on some test statistic, which I'll talk about in a minute. So what does that look like? So here is a histogram of if we have some T hat, which is some measure of how different the two samples are, even if the two distributions are the same because of random noise, probably the samples are not going to be identical, right? And so our T hat is not going to be 0 usually, even if the two underlying distributions are actually the same. So we'll have some distribution of what T hat might look like given two samples from the same distribution P equals Q. We'll also have some distribution of what this estimator will look like in the setting where they're different. So these curves here are like the probability density for one particular estimator T hat for one particular distribution in the P equals Q case, and for one particular pair of distributions in the P not equal Q case. So in the null hypothesis testing framework, we want to choose some threshold on T hat where if T hat is bigger than that threshold, then we'll reject the null hypothesis. We'll say we're pretty sure that it's unlikely to have seen such a big T hat if they were actually the same. And we're going to choose that by controlling the false rejection rate, the type 1 error. We want the total probability of T hat lying to the right of this threshold to be at most some number alpha, usually say 0.05. Now, the other important quantity of a test is the power. That's the true rejection rate. It's easy to come up with a test that never has a false rejection rate if you just never reject, right? But we want a test that rejects the null hypothesis when it's not true as much as we can, subject to the constraint of the false rejection rate being less than null. So we need to find this threshold somehow for a particular estimator function t hat. And the way we're usually going to do that, at least in this talk today, is with something called permutation testing, which isn't going to be super important to understand the talk. But basically all we do is we say, well, we have these samples, x1, x2, x3, whatever, and the y's. But under the null distribution, these are all samples from the same distribution, right? So if we just mix them up and we pretend that some of the points are x and we just mix together the x's and the y's, then this will be, it turns out, if you do a theorem, that this will estimate the distribution of the test statistic when p equals q. So you just do this for a bunch of different permutations, get the test statistic estimator, get a quantile of that distribution. That's how we set C alpha. Okay, that's all we're going to say about C alpha for today, setting the threshold. Now, that'll work for any test statistic t hat that we want. So we need to choose some t hat, right? The t hat that we're going to work with today is called the maximum mean discrepancy, the MMD. And we're going to define what that is. To get there, we're going to note that the MMD is a kernel-based distance between distributions. And of course, 10 years ago, I wouldn't have had to remind anyone what a kernel is. But these days, maybe not everyone has it on the tip of their fingers. What is a kernel? So what's a kernel? So a linear classifier, as you probably remember, is just a classifier that is linear in the input space, right? So here we have a 1D classification problem. We have like some blue points, some orange points. We want to separate the blue points from the orange points. A linear classifier is just going to be a threshold in 1D, and we can't separate the 2 points, the 2 sets very well with a linear classifier. So the idea in a kernel, the idea leading to a kernel is we want to augment the data somehow. In this case, we can do like a polynomial kernel, where if we put in the x squared features as well, then we map that 1D data into this 2D space, or potentially a 3D space with this intercept term, whatever, don't worry about it. And then a linear classifier in this 2D space is actually a much more powerful classifier in the original space. So that's what we do. We map things to some feature representation phi, but the idea of the kernel trick is that we can avoid explicitly writing out and choosing this feature mapping if we instead choose a kernel function, where the kernel function is just the inner product, the dot product between those features. And a kernelized algorithm, so like a kernel SVM or kernel logistic regression or whatever algorithm you want to do, including the MMD, is going to access the data only in terms of the kernel, in terms of these inner products. A kernel also introduces some notion of smoothness on functions, depending on the kernel. And so what does that look like? So if we choose a kernel like the Gaussian Rbf kernel, which is kind of the canonical kernel, that's usually the default example, that kind of looks like this if we're in, this is the point where x equals y, and then this is moving away where x moves farther away from y. This is what this function looks like, keeping x fixed and moving y around. So what does this kernel lead to in terms of like this notion of a norm? So some functions that are smooth with respect to this kernel norm might look like this. They have some wiggles. The scale of the wiggling is kind of around roughly the scale of sigma in this Gaussian kernel. Okay, now that we have this tool of the kernel norm, we're going to define the MMD in this way. So what we're doing here is this is the distance between distributions, P and Q, in terms of some kernel. So the way we define this is we have some critic function f, and we want this function to be large on average on samples from P and small on average on samples from Q. So it's able to kind of tell the difference between the P samples and the Q samples. What does that look like? Well, it turns out, oh, and also this critic function should be smooth with respect to the kernel. If we were allowed to do any function, then this would usually just be infinity, right? Because any point where they're different, we could just yank the function way up to be infinitely big. So we need some kind of constraint on these functions. And the constraint we make in the in the case of the MMD is that we want the kernel norm of that function to be small. So if you do some math, which is not very hard, but I'm not going to do it today, it turns out that this supremum is actually achieved by a function that looks like this. So what does that look like? So let's take some 1D points here where we have a discrete distribution that's just uniform over these blue points for P and uniform over these orange points for Q. So, and we use a Gaussian kernel that looks like this. Here's the kernel centered at this point. To get this supremum function, what we do is we just put one of these Gaussian bumps at each data point. And then we add them up. And then we take the difference between those two things. So this blue dashed line is this part of the function. The orange one is this part. And the difference is this green line. So this is a function that on average is high on the blue points and small on the orange points. So this difference is large, but the function is also smooth with the notion of smoothness given by the Gaussian kernel. So the choice of kernel here is really important, actually. In this Gaussian kernel, there's this parameter, which is the length scale, right? So this is the critic function you get with this length scale. If you choose too big of a length scale, then the smooth functions are all really flat. So this is constraining our function to be kind of too smooth. And we get this kernel, this critic function that doesn't really do much. Or if we allow our functions to be bumpier, if we choose a smaller length scale, then we would get a function like this pink one that is really, really wiggly, right? And this probably isn't going to generalize well to new samples from the same distribution. Okay. If you take this function and you plug it back in with the kind of proportionality constant worked out, then this is a form, this is what you get for the MMD. It's this expectation of the kernels like this. So what does that look like? Well, that leads us to a very natural notion of how to estimate the MMD based on samples. So if we have some sample points X, this first term is the average kernel like between X points. So we can make this kernel matrix of how similar the inputs X are to each other. We just take the average of that kernel matrix that estimates this first term. We do the same thing for the Y samples, and then we do a cross similarity term that's the same across. And then that's our estimator based on samples. I'm actually going to skip. Okay. So the MMD can also be thought of as matching the features of these feature maps, phi, between the two distributions. So for a linear kernel, like this very simple kernel that's just a dot product, this feature map is just the identity. And then the MMD just becomes the distance between the means of the distributions. So that's very simple. But for most interesting kernels, this phi function is much more complicated. And so for like the Gaussian kernel, this phi function is actually infinite dimensional. And so you're matching infinitely many of these features on average. It turns out for many of these kernels with infinite dimensional features, like the Gaussian, it's a thing called characteristic, means that the MMD is 0 if and only if the distributions are exactly the same. So for the Gaussian kernel, this is true. You can also do permutation testing pretty efficiently. And then you can run your test. These are what the asymptotics look like, not going to matter too much to us for right now. And basically what happens is that with any characteristic kernel, you get a consistent test. And so given enough samples, you can always distinguish the case where the MMD is 0, meaning the two distributions are the same, from the case where it's not 0, the two distributions are different. But this is an asymptotic property with infinitely many samples. For if you just choose a Gaussian kernel and then say, okay, I'm done, it's characteristic, this might not happen until you have huge numbers of samples. And so for practical things, it's really important to pick the right kernel. So how do we go about picking the right kernel? So here's one way to pick a kernel, which isn't obvious at first that it's a kernel. It was proposed, a very natural idea, not in the MMD framework, but we'll see in a second that it is a kernel. So the idea of classifier to sample tests is basically you take your data that you're given, your X and your Y, and you divide it into like a training half and a testing half. On half the data, this red half, you go and you train a classifier to distinguish X from Y. So you give it the labels +1 if it's from X and -1 if it's from Y, and then train a classifier to tell them apart. Then you take that classifier and you evaluate it on this held out test set. If the two distributions are the same, this classification problem is impossible, right? And so your accuracy will be like roughly 50%. It'll be binomial around 50%, right? If you choose as your kernel this thing, basically you just multiply the outcome of the binary classifier, then it turns out that the MMD value is exactly like monotonic in the accuracy of the classifier. So this classifier to sample test is a special case of the MMD with this particular kernel. This is kind of a weird kernel because this is a deep network or whatever classifier that you trained, right? This isn't something where you can just write it down in advance. Okay, this is the kernel I want to use. This is something you're training on the data and then using. That's kind of a key idea of getting kernel methods to work really well. It's by doing what I at least call like deep kernels. So you can do this more generally, where if you think about it, a deep learning model usually has a linear layer at the end, right? So you can think of it as being a linear model, like a linear classifier or regressor or whatever, in some feature space, which is a learned feature space, which is all of the network up until the last layer, right? And so for a fixed network up until the last layer, we can think of this our final function f as being a kernel, like being in the RKHS of some kernel, where the kernel is defined by the network up until that point. If you're familiar with the NNGP approximation to like the NNGP kernel approximation to training neural networks, this is the same idea. But this kind of naturally points out we can actually generalize this idea. There's no reason that the kernel has to look like this. Actually, it could look like anything. It doesn't have to be linear on this last layer of the neural network. It could be some nonlinear kernel of these feature representations that have been extracted from the data. So you can take like a Gaussian kernel or something on top of the kernel here, or the feature map learned here. And it's worth pointing out that normal deep learning using like this kernel that we saw before, if your F thing, this means that using like this deep kernel framework includes normal deep learning, where your deep kernel is just take the function to define the kernel like this, right? You could use this 1/4, you could not. If you have this RKHS, then the final function that you learn in the RPHS is just going to be some scalar multiple of the original function. If you add a constant to this kernel, then you get you could get an affine function of this original thing. And if your f is like a continuous output, meaning the logit rather than the hard ±1 decision, then this is just Platt scaling. So you can think of deep kernels with this particular choice of kernel as just Platt scaling your, so calibrating your learned kernel on a test set. If this doesn't make sense, don't worry about it. This is just a connection that, I don't know, I think is cool, but often people are confused by it. So don't worry about it. Okay, this is kind of tangential to the talk, but I just want to briefly point out, this doesn't mean that deep learning is a kernel method, because you aren't fixing the kernel ahead of time. And so that this doesn't provide, I think, any meaningful connection between deep learning and saying, oh, I can explain deep learning in terms of kernels. But deep kernels are not regular kernels in exactly the same way that deep learning is not a linear model, right? The relationship is exactly the same. So, yeah. Okay, that was kind of an aside. Anyway, we now have this concept of deep kernels, meaning we have kernels with a lot of parameters in them, right? All the parameters of a neural network. And we want to choose those parameters somehow to work well to give us a good MMD test. This is exactly in the same way that back in, so when we're training a classifier, you can think of it in the kernel framework as choosing the parameters of this kernel to give us a good test, right? So in the classifier framework, we're doing it in order to choose some, in order to optimize the cross entropy loss or whatever, right? But in the MMD testing framework, we can actually see from the asymptotics of MMD, it's just a few lines, to see that the power of the MMD test is approximately this form. So what is this form? So this phi function, first of all, is the CDF of a standard normal. So that's just a simple monotonic function, right? This is the MMD between the two distributions. This sigma is the standard deviation of the MMD estimator, the asymptotic standard deviation of the MMD estimator. That's just some number that actually doesn't depend on n because the variance just decays like we're dead. Also, C alpha is the threshold that we get from permutation testing. In the asymptotics of MMD, we choose this scaling such that C alpha is a constant. So in this expression, basically everything, so MMD, sigma, and C alpha all don't depend on n. And so this expression is generally going to be dominated by this term, right? If we're trying to maximize it, if we have a good MMD and a small variance, then we'll have a good test, and this part doesn't really matter so much. So what that means is we can choose our kernel to get the most powerful test if we just maximize some estimate of this term, the MMD squared over the standard deviation of the estimator of MMD squared. So we already know how to estimate MMD. That was just the kernel matrix averages thing. It turns out you can also get a nice simple estimator of sigma hat by kind of looking at the form of MMD and using U statistics, the theory of U statistics, which is a well understood thing. And you get some expression that is the same computational complexity as computing the MMD estimator itself. Then if you just plug those two estimators in and divide them, you can prove that MMD hat over sigma hat converges uniformly to MMD squared over sigma. And so you can estimate this thing, which is going to approximately minimize, or maximize, sorry, is going to approximately maximize this power, which is the power of your test. And so we have a way that we can find the most powerful test, just like we have a loss function that we can implement in PyTorch or whatever to then just optimize to get the most powerful test. So here's an example of kind of a toy problem for MMD tests. On the left, this is the distribution P. The distribution is itself just distributed on this kind of grid of standard normals. On the right is a sample from the distribution Q. This is a mixture also of Gaussians, kind of on a grid, but these Gaussians have different correlations at different points. If we learn, so the normal MMD test, if we use like a Gaussian kernel, these are the contours of the kernels centered at the center of each block. So this kernel kind of doesn't know the geometry of the space at all. It just knows a single length scale, right? But if we have a deep kernel where we put some parameters in and we optimize those parameters, we can learn the geometry of the space so that we can see, okay, well, I know that these Gaussians over here correlated this way, these ones are correlated this way, this one is mostly not that correlated, and we can learn the space, and that's going to give us a more powerful test between these two distributions, the blue and the red distributions here. So here's a plot of the power. Here, the number of samples is increasing to the right. So if we have very few samples, no method is going to work. If we have a ton of samples, every method is going to work. But in between, this MMD with the optimized deep kernel works somewhat better than MMD with an optimized Gaussian kernel. It's not on this plot, but if you just do kind of the default thing most people do for MMD tests, so just take what's called the median heuristic, you get a power that's like really bad. It's like down here somewhere. And then these are some other methods for two sample tests that do some kernel learning in them as well, that we do much better. Okay, I'm gonna skip this because it takes too long to explain. Okay, so here's a more interesting problem. I'm not gonna go explain it in full, but there's this thing called CFAR 10.1, which was an attempt to replicate the CFAR 10 dataset, kind of for like learning theory reasons. They wanted to do some experiments to see if they could get a fresh sample from CFAR 10.1. And they got some weird results and wanted to know, okay, is the CFAR 10.1 that we tried to replicate actually the same as CFAR 10? In the paper, which I forgot to put a citation here, but I think it's Recht et al. They were not able to confidently say that these two distributions are different. They tried to train a classifier between them, and they couldn't get like a 95% confidence interval to reliably distinguish the two sets. We, with our method, are able to distinguish the two sets 75% of the time, using only like half the samples and then repeating 10 times. So that's what the randomness is. But on like 75% of the runs, we were able to reject the null distribution, which is much more powerful than like a classifier test or various other tests that don't do this optimized deep kernel stuff. Okay. We also work reliably better than classifier-based tests across a bunch of different problems. And yeah, so this is a better method, it seems, than classifier-based approaches in lots of settings. Okay, so that's the basic idea of two-sample testing with deep kernels. And that's kind of the main thing I wanted to teach in this talk. In the remaining chunk of time, I'm going to talk quickly about two projects that are recent projects that extended this to kind of take this to new places and whatever. But this basic algorithm of just maximizing this power I think it's the thing that you should take away and you should think about using in your own settings for sure. So here's some like recent stuff, kind of extending this framework. So, yeah, sorry, is there a question?
Excuse me, thank you for your sharing. And in the previous slide, you talk about the rejection rate, a very good rejection rate. Does this connect to the true rejection rate or the false rejection rate in your earlier slide?
So here, this is the rejection rate when you actually distinguish CFAR10 from CFAR10.1. I didn't show the results here, but if you just mix the two distributions together and then try to distinguish a random half from a random half, you get the right, I think this is at a 0.05 level. So this should be a true rejection because we are reliably able to say the distributions are different.
Thank you for your clarification.
Okay, so this method works really well if you have a decent amount of data to train a deep kernel. But a lot of times you might not have that much data to use to train like a, to train a whole network from scratch on your particular problem. Especially because you have to kind of divide the data in half or divide it somehow between the training and the testing part, right? Because you need enough data to train the parameters of your kernel. You also need enough data that if it's a small difference between the distributions, you need enough test data to be able to reliably say, yeah, it's not just random noise, right? So we need lots of data potentially to be able to detect these things. And how to divide between this training part and this test part depends both on how good is the best kernel and how hard is it to find the best kernel. We don't know either of those things ahead of time. And we can't try more than one split because then we're doing multiple testing, we have to correct them. So we do actually need like a decent amount of data to be able to do this stuff on complicated distribution. So one idea for how to kind of handle having smaller amounts of data is thinking about what if we don't have that much data for the testing problem we want to do, but we do have a bunch of related problems. So in this setup, we're assuming a setup kind of similar to meta-learning, where if you're not familiar with meta-learning, basically the idea is you want to learn at train time, you want to find an algorithm that is able to see, okay, here is an example of a seagull, and I don't know what kind of bird this is, I should look it up. And then given very small numbers, like maybe just literally one gull and one whatever this is, then get a classifier that works well to distinguish these. And then in another episode, we give it totally different classes and ask it to distinguish those classes. And then we keep doing that a lot of times, and we train a classification algorithm. We learn to learn on these problems that are like related classification problems. Then at test time, we give it totally new things that it's never seen before. And we look, okay, how good is it at distinguishing, again, I should have looked these up, whatever kind of bird this is versus this kind of duck. Like how good is our classifier then at new classes it's never seen before. So in the testing setting, this is kind of like that, right? What we want is we want to find an algorithm that we give it a testing problem and it finds a powerful kernel on that problem. And we give it another testing problem and it finds a powerful kernel, et cetera, et cetera, et cetera. And it uses that experience somehow to find a powerful kernel for a new task with limited data. So taking as an example, this CFAR10 versus CFAR10.1 problem, where are we going to get related data from? Because CFAR10 has plenty of images in it, right? It's 60,000. But 10.1 only has 2,000 images in it. And it turns out that's enough, but it's really not that many, right? And so it makes sense in this setting that we might want to get related data from somewhere else. So where do we get that from? Well, there's a lot of potential options. But one option would be to just use chunks of CFAR10 that we're otherwise not using, right? And so one particular thing we could do is we could find a kernel to distinguish different classes of CFAR10, because that's easily at hand, right? We can distinguish airplanes versus cars, airplanes versus birds, just kind of every pair or a sample of pairs or whatever of CFAR10 problem. And then using this experience somehow, we will then hopefully be able to distinguish CFAR10 from CFAR10.1 without using very many samples. So here's one approach, which we propose in our paper. If you're familiar with MAML, this is very inspired by MAML. Basically, what we're going to do is we have some algorithm, A theta, which is some parameterized algorithm that gets in like a meta training sample and outputs some kernel. And we're going to train the parameters of that algorithm to maximize the power. This J refers to the MMD over its variance. We're going to maximize the power of that kernel on the meta test set during this meta training phase to choose the parameters of this algorithm. So what are the parameters of this algorithm? Well, maybe it's like running 5 steps of gradient descent, starting at some initialization. And so we're going to learn the initialization. We could learn the step size, stuff like that. So we do this at meta training time. And then for the test that we actually want to do, we still split the data. We apply that algorithm to pick a kernel on the training part of this test data. And then we run that test on the test part. And this is our final test. This algorithm works. It works a lot better than not doing anything, but it turns out it doesn't work as well as we had hoped it would. This might be because, unlike in regular meta learning, you can actually find a kernel, like an initialization here, that just works pretty well on every problem we give it. And so it may not actually do that much adaptation on this data, like the support set. Okay, so another approach we can take, rather than that MAML-like approach, is we do something that we call Meta-Mkl. So multiple kernel learning. Basically what we do in this framework is on each of the related tasks, we're going to learn the best kernel we can learn on that related task. Just totally independently, just using the approach from the previous part of the talk. Then we learn a bunch of kernels. And then we now have a bunch of good kernels on related problems kind of in our arsenal to use at test time. And so then what we do at test time is we split the data as before, and we learn a linear combination of these base kernels for this particular test task. Then we can run a test using this linear combination of kernels, which is going to be much easier to learn on our test data than learning a whole neural network from scratch, right? Because we're only learning the weights of the linear combination. We're not learning all of the parameters of a neural network. That method, we can do some theoretical analysis. I'm not going to go into any details, but basically it works a lot better, even though the big O in terms of the number of samples is the same. It separates out the multiplier based on the size of the network, like the complexity of the network you're learning. And the thing that's multiplied by the test size is just how many meta training tasks you have. So you can learn that much faster. Yeah. So here's some results for the CFAR 10.1. And this is now with, so if, for example, we take a bunch of these related tasks, but then we give it, okay, 100 points to choose a kernel with and 500 points to actually run the test with. So we get 600 total test points from CFAR 10.1. Then the previous methods only get really pretty bad power, right? So our method is still the best, but that's 22% rejection rate. Whereas if we do this meta thing, we can get 73% with just very few samples from CPR 10.1. And if we use more samples, we get really high powers, whereas without using the metadata at all, the amount of power you get is much lower. We also do, it's not just that we're using more data from CPR 10. This aggregate kernel learning thing is doing kernel learning, using all of the data that was available, like that was the metatask ever sees. And it does much better than not using that data, but it's still much worse than the meta approaches. So doing the meta stuff actually helps a lot more than just having access to that data. Okay, very quickly, I'm going to talk about one last thing. So we now have a good method for learning kernels. We can even do it in this kind of meta task if we have a limited amount of data. But the question that I kind of restricted myself to at the start of the talk is just saying, is P exactly equal to Q? And a lot of times we kind of know in advance that they're not exactly equal. And so, the test isn't necessarily going to tell us anything interesting because we know they're different in a way that we don't care about. So for example, this is the thing I skipped talking about, but when we first ran kind of criticism of a generative model on MNIST, the first thing that it did was it just realized, hey, this GAN is outputting numbers that aren't, MNIST only has 256 distinct values for pixels because it's stored as like a uint8, right? The GAN outputs in float 32s, and so it actually outputs a lot of numbers that are not the same exact numbers that MNIST outputs. And so if you see a number that isn't one of the 256 numbers that MNIST has, then you know right away that it can't be an MNIST sample, right? So in that case, because we understand that difference, it's simple to deal with. And so in that case, we just kind of rounded the pixels to just be 0 or 1, and then that dodges this problem. But a lot of times there might be more complicated problems where we can't address it so easily. So it would be, sorry, okay, there we go. Sorry, my computer just freaked out. Okay, so it would be nice if we could find a kernel that is able to distinguish the thing we want to distinguish, but can't distinguish some constructed set that I'm going to call PS and QS that are like a difference that we know we don't want to care about. If we construct some distributions that like basically have this kind of stupid difference between them, and we can choose a kernel that we know can't look at that kind of stupid difference, then if it can still distinguish the target that we're looking for, then that would be nice, right? This is also useful for like fair representation learning. So for example, if you want to be able to say, okay, who should I loan to without using a representation that is able to tell people apart by race. And then that is, one version of a fairness criterion to, it's a desirable property sometimes. Okay, just because I'll go quickly. So what we would want is if this rho is some notion of power, we want something that minimizes this term. So this is the power on the sensitive pair, and this is the power on the target pair. So the way to minimize this is if this power is 0 and this power is 1, then this will be -1, and that's what we want. So the first thing you could try is just using the same thing we were maximizing before, this MMD squared over its standard deviation. This doesn't work, unfortunately. And the reason it doesn't work is a lot of times it hits to a place where, okay, I have 99% power on the target task. I have 90% power on the sensitive task. And I want to just keep really, really, really improving this ratio on the target task which is going to bring my power from like 0.99 to 0.993 or whatever, without worrying about this. So that's not good because it doesn't balance between the two objectives appropriately. So the second idea is to use actually the full power estimate, right? Then this is the actual power, and that's what we want. We can estimate this by just doing the permutation testing inside our loss function. And if you just do it straightforwardly, then that's totally fine. This works better, but it tends to kind of stall out in getting the sensitive power low. I think, we don't know this for sure, but we believe that this is probably because of the dependence between these two estimators, doing it on the same data. Yeah. So what we actually do is something a little different. So there's something called the block estimator of the MMD, which is instead of computing the whole kernel matrix, you just divide it up into blocks of data points. And on each of those blocks, you compute the full kernel. Right? But you never compute the kernel value across blocks. You just take the MMD on this block, the MMD on this block, the MMD on this block, and then you average them out. The asymptotics of each of these blocks we understand, because that's the asymptotics we saw before, as each of these blocks grows. But we have a nice, simple central limit theorem, because it's just the average of independent things across the blocks. And so if you do it out, the power ends up looking like this, where this C alpha term is now really simple. We don't have to do permutation testing anymore. This is just like if we use alpha 0.05, then this is just a constant 1.96. So our algorithm, we call MMD B fair, the B is for block. We do this minimizer where this is the power of a block test with B blocks of size big B. But these blocks and their size doesn't have anything to do with the data that we're actually estimating it on mini batches. We're just picking some numbers here. They're just hyperparameters of our objective function. And we don't actually use any blocking computation. But optimizing this works. We can also do this for representation learning. In the interest of time, I'm going to skip talking about any details there. But we can do this to try to learn a representation that no kernel can distinguish. So we evaluate this on two data sets. Adult is like a census data metadata, and you're trying to predict people's income while being fair with respect to their age. And Shapes 3D is a vision data set where there's lots of shapes of different colors with different, the floor is a color and the background is a color and orientation and all kinds of stuff. And so, for example, here, we're trying to distinguish squares or cubes versus spheres without being able to distinguish red objects versus cyan objects. If we do that, we do a better job at learning representations that don't get this power than kind of fairness-based methods. These other methods for like fair representation learning. We're also able to do it for multiple things at once, but there's some challenges. So for example, when S and T are very correlated, the method doesn't work very well because we're asking it to, like the power, the sets we're feeding it are very, very similar between the two things. Okay, there's also more to do in terms of meta testing. There's some interpretability things, but I'm over time, I think, so I won't talk about those. And there's some other stuff we could do. Okay, I will just leave with this inspiring quote from 2007 about deep kernels, not specifically about testing, basically saying deep kernels are a good idea from Benjio and Lipkin. Okay, so that's what I wanted to talk about, and I'm happy to take any questions at this point. Thank you.
Thank you for your great talk. Yeah, yes, please go ahead.
Yeah, thank you for your sharing today. I'm wondering that during your meta learning approach, you don't need to introduce any new data, and why this meta-learning works even better than the previous approach, given there is no additional data?
So there is actually additional data in that. So, okay, so in this table, I didn't talk about it in detail. This is the previous approach with a deep kernel, where we're just giving it, so like for this column, we're just giving it 300 points from CFAR 10 and 300 points from 10.1. In this version, we're actually looking at, I think, all 60,000 points from CFAR 10 and 300 points from CFAR 10.1. So we are actually looking at a lot more data. This is the version where we give it this, basically, okay, so in this version, we're just giving it 300 points from each and then optimizing on that. In this version, we're giving it 60,000 points from CFAR 10 and 300 points from 10.1. In this case, I think the reason for this gap, where here they're looking at the same set of data, but the meta one still does much better. I think the reason there is basically some kind of like, it's giving it more kind of implicit regularization about what kind of kernel it should find. Here it's learning lots of kernels to distinguish things. It's learning powerful kernels in the meta training step. It sees lots of data points on both sides of this problem. And it's trying to learn kernels that work well with lots of data points on both sides. Whereas in this version, it's seeing 60,000 CFAR 10 points, but it's only seeing 310.1 points. And so it's probably overfitting to the 10.1 points much more quickly than this one is my guess.
I see, thank you so much.
Basically, I have a question. For example, we know that in current work, adversarial data is visually similar to the natural data. Adversarial data is based on the model we optimize to generate some data. It's basically visualized to it's visually visualized to seem to our eyes. It's like the natural data. I'm wondering, other from the statistic, the distributionally is the same or different? What do you think of this?
Yeah, so actually I haven't worked on that, but Feng, who's here, has. He wrote a paper specifically about MMD recognizing adversarial attacks. Let me see if I can pull up the title here.
Yes.
Oh, you're on that. Yes. So
yeah.
absolutely. Yeah. Okay. I guess you know that work better than I do, obviously.
Yeah.
So,
I just want to maybe think it's kind of like sometimes is unconcluded. Sometimes it's unconcluded. Basically, recently we also have a work to show that two-sample test is also subset is also vulnerable to adversarial attack. For example, we have this mechanism.
Sure.
Yeah, then we can uncover the potential threat model. Then can make the two-sample test fail. Yeah, so it kind of like yeah, it's a little bit unconcluded. I really want to hear your opinion. Yeah.
I see.
Yeah.
Yeah. Sorry, I misunderstood what you were asking at first. So definitely this process is like this process of learning an optimized kernel. I'm sure you can attack that process and get adversarial attacks that then break it.
Yes.
The meta version might be a little, I don't know, maybe that's not true. Maybe the meta version would be a little more robust, but maybe not, I don't know. There's some work out there, I'm not super familiar with it, on robust versions of the MMD or related estimators. And so it might be that plugging in just like a robust estimator of the MMD, you might be able to do all of this stuff, being robust to contaminating 1% of the data or whatever.
I see.
But I haven't really thought about that.
I see. Okay. Thank you very much. Yeah. All right. Is there any questions from our audience? Yeah. If no, let's again for our valuable guest, Danica, to come here to give her wonderful talks. We actually learned quite a lot. In the future, when the situation lifted, we sincerely welcome you to visit us in Tokyo in our Nihonbashi office. It's basically in the center of the Tokyo. It's near the Jinja. Our office is a wonderful place. So when you have free time, when the situation is lifted, please visit us.
Yeah, I would love to do that. Yeah.
Thank you again. Thank you very much for your great talk. Bye-bye. All right. Hi, Yinpeng, are you there?
Hi, I'm here.
Great. Should I introduce you first? Then you can proceed your talk.
Okay.
Great. Yinpeng Dong received his BE and PhD degree from Tsinghua University in 2017 and 2022, advised by Professor Zhu Jun. His research interests includes machine learning, deep learning, especially the adversarial robustness of deep learning. Yinpeng has published over 20 papers in prestigious conferences and journals, including TPAMI, IGCV, CVPR, NeurIPS. He served as a reviewer for multiple conferences and journals. He received several awards, including China National Scholarship, Tsinghua Future PhD Fellowship, Microsoft Research Asia Fellowship, Baidu Fellowship. He won all the 3 tasks in NeurIPS 2017 adversarial attacks and defense as a team leader for the 2 attack tasks. Let's sincerely welcome Yinpeng to give his talk, Black Box Adversarial Attacks, from Theory to Practice. Hi, Yinpeng, please proceed.
Hi. Thanks, Yinpeng, for introducing me. Can you see my slide?
Yes, can see your slides and also hear your voice.
Okay. Hello, everyone. I'm very thankful Yinpeng for inviting me to give a talk at the TrustML Young Scientist Seminars. So my name is Yinpeng Dong. I'm now a postdoctoral researcher in the Department of Computer Science and Technology, Tsinghua University. I'm also a research scientist at UI, which is a startup company focusing on trustworthy artificial intelligence. So the topic of my presentation is black box adversarial attack from theory to practice. So in this talk, I would like to introduce some of our works in recent years on black box adversarial attacks from both the theoretical and the empirical perspectives. Okay, let's start. First, I would like to briefly introduce some background. So in the past decades, artificial intelligence and especially machine learning and deep learning techniques has achieved great progress in various fields, including computer vision, natural language processing, and playing games. Artificial intelligence has greatly changed our life and making our life more efficient and convenient. AI has the potential to revolutionize how we live, work, learn, discover, and communicate. Despite the success achieved by machine learning and deep learning models, we need to ask ourselves, is ML or DL really ready for real-world deployment? Most of the machine learning algorithms have an underlying assumption that the data points are independently and identically distributed. Such an IID assumption may be unrealistic in real-world applications. Typically, we usually measure the performance of an ML model by calculating the fraction of mistakes of the testing data, which are sampled from the same data distribution, and we compare the performance of different ML models to evaluate their performance. However, in reality, when a machine learning model is deployed in the real-world applications, it needs to deal with the data that does not come from the training data distribution. This is called the distributional shift or domain shift problem in machine learning, which is a hot research topic. For testing data that breaks the IID assumption, the existing machine learning models usually lack the robustness. Deep learning models are known to be vulnerable to adversarial examples. Adversarial examples are maliciously generated by adversaries by adding various small noises to the natural examples, but can fool a model to produce wrong predictions. So in this slide, I show two adversarial examples for image classification. So in the left column, we show two natural examples which can be correctly predicted by an image classifier. And the middle column shows the adversarial perturbations generated by some adversarials designed algorithms. So by adding the adversarial perturbations to the original examples, we can actually get the adversarial examples shown in the right column. We can see that the adversarial examples looks very similar to the original ones, and they are often indistinguishable. But the image classifier can make wrong predictions with very high confidence. Adversarial examples also exist in the real world. For example, the adversarial examples can be crafted for route-sum classification systems in autonomous driving and face recognition models. So the existence of adversarial examples may cause very severe security threats in real-world applications. Adversarial attacks has attracted a lot of attention in recent years, which aim to generate adversarial examples with high success rate and high efficiency. So adversarial attacks can help us truly understand the weaknesses of the current machine learning systems, evaluate the robustness of these models, and may help us develop more robust deep learning models. For example, adversarial training use adversarial attacks to generate adversarial examples and use these adversarial examples to build more robust models. So studying adversarial attacks is a hot research topic in recent years. Formerly, generating adversarial examples can be considered as a constraint optimization problem. For a natural example X, we aim to generate an adversarial example X star that maximizes the loss function L, because we want to let the model output a wrong prediction for X star. We also constrain the LP norm between the adversarial example and the natural one to be smaller than a threshold, which is called the perturbation budget, epsilon. We usually use the L infinity and the L2 norms. There are several attack methods proposed to solve these optimization problems. For example, the famous fast gradient sum method adopts a one-step update to get an adversarial example. FGSM first calculates the gradient of the loss function with respect to the input X, and then multiply the perturbation budget epsilon with the sum of the gradient, such that the noise is normalized under the L infinity norm constraint. And the FGSM then directly adds the noise to the original example to get the adversarial example. Based on FGSM, the basic iterative method takes multiple small gradient updates to generate adversarial examples. And the adversarial example can also be generated by some optimization-based methods, which optimize an unconstrained objective function to generate adversarial examples. Note that this attack method all need the gradient of the loss function with respect to the input. So they are called white box attacks. However, in many real-world applications, we cannot get any information of the target model. For example, for real-world face recognition models, we cannot get its model architectures or parameters. So we need to attack them in the black box manner. So the key problem here is how to solve this optimization problem when the gradient is unavailable. There are two lines of works on black box attacks. The first one is based on the transferability of adversarial examples. It has been found that the adversarial examples crafted for one model can also fool a different model. So we can attack the black box model using the adversarial examples generated for a substitute white box model. The second one is based on gradient-free optimization method, which basically needs to query the black box model and obtain the corresponding outputs. For score-based adversarial attack, the model can obtain the output probabilities over all classes for a query input. So the adversary, even if the adversary do not know the gradient of the black box model, the gradient can be estimated by some finite difference based method. For decision-based adversarial attack, the model only outputs the hard label for a query. So the adversarial example can also be generated on the decision boundary of a model, mainly based on some heuristic search method. We have done some work on transfer-based attack. So I will introduce some of our works in transfer-based attack first. The goal of transfer-based attack is to improve the transferability of adversarial examples, such that the adversarial examples can fool the black box models more effectively. So our main idea of transfer-based attack is to take a meta perspective. So we can make an analogy between generating adversarial examples and training machine learning models, because both of them can be formulated as solving optimization problems. So in generating adversarial examples, we think that we use white box models to generate adversarial examples, and then we test the transferability of the adversarial examples on black box models. This is similar to training machine learning models. In training, we use some training data to train the model parameters, and after training, we directly test the generalization performance on the testing data. So if we make an analogy between generating adversarial examples and training machine learning models, we actually make similar analogies between white box models and training data, black box models and testing data, and also the transferability and the generalizability of machine learning models. So in this way, we can leverage some useful techniques that are designed for improving model generalization, for improving the adversarial transferability. So this is the main idea of transfer-based attacks. For the existing adversarial attack method, we observe that there is a trade-off between the black box transferability and the white box attack ability of some previous method. This can make the black box attack ineffective. To successfully fool a black box model, we need to generate an adversarial example which first fool the white box model and second transfer to the black box model. So in particular, the fast gradient descent method has very poor white box attack ability because it is a one-step method with insufficient optimization. And the iterative-based method are very strong to attack the white box model, but they usually lead to poor transferability. The reason is that the adversarial example generated by iterative method is very sensitive to the white box model, and maybe in other words, it overfits the white box model, so it cannot transfer to other black box models. So the existing methods are not effective for black box attack. So the key challenge here is how to make adversarial example less sensitive to the white box model being attacked. And in other words, it means that we need to make adversarial examples not overfit to the current model and improve its generalization or transferability to other black box models. To solve this problem, we propose some method for transfer-based adversarial attacks. So the first method is published at CVPR 2018. We propose a momentum iterative method. This method is very simple, which integrates a momentum term into the iterative attack method. So in the attack process, we use GT to accumulate the gradient information of the past iterations, and we generate adversarial examples based on the accumulated gradient. So the momentum term can help to stabilize update directions and escape from poor local optima during the attack iterations, and it can help to solve the overfitting problem and improve the transferability for other black box models. So the method is very simple and is also very effective. Here we show some results of black box attack on the ImageNet models. So here we consider some typical ImageNet models like Inception V3, Inception V4, and RISNet. And we also consider some adversarially trained models. Here we generate adversarial examples based on different methods, including fast gradient set method and the iterative method and our proposed momentum-based method. And we use this attack to generate adversarial examples against several white box models. And we directly test the attack success rate against all these black box models. So in this table, we can see that the success rate achieved by our method is much higher than that of the baseline method. We usually achieve about twice of the success rate compared with the baseline methods. So we also use this method to win the NURBS 2017 adversarial attack competitions. Here I would like to introduce our second work on transfer-based adversarial attack. So this paper is published at CVPR 2019. So in this paper, we consider adversarial attacks against the defense models. So due to the threat of adversarial examples, many defense methods have been proposed to improve the robustness of deep learning models. So we aim to develop more effective transfer-based attack against the defense models to study their robustness under the black box setting. First, we observe that the discriminative regions, which are visualized by the attention maps of the defenses, are significantly different from the normally trained models. Recall that we usually adopt gradient-based method to craft adversarial examples. So the adversarial examples will be highly sensitive to the discriminative region of the white box model and hard to remain adversarial for other black box defense models. So to address this problem, we propose to optimize an adversarial example or an ensemble of image transformations. So this formulation is very similar to the typical expectation or transformation method. This expectation or transformation is proposed to generate physical adversarial examples which are robust to different image transformations. But our goal here is to improve the transferability of adversarial examples by addressing the overfitting problem. And in this paper, we only consider the image translation operation only, because we know that convolutional neural network has the translation invariance property. So we can use this translation invariant property to develop a very efficient algorithm to solve this optimization problem. For gradient calculation, we assume that the translation invariant property of convolutional neural networks is holds. So we can approximate the gradient of our attack objective function by convolving the gradient as the untranslated image with a predefined kernel matrix. So we can see that by approximating the gradient, we actually need to calculate the gradient of the loss function with respect to only one input, and then we can get the approximate gradient of our objective function by convolving the gradient with a predefined kernel. So generally speaking, we can use any kernel matrix here, but in this work, we introduce 3 different kernel matrices, including uniform, linear, and Gaussian kernel. And our method can be integrated into any gradient-based attack method. So by integrating our method with previous method, we only need to change the raw gradient of the baseline method with our derived gradient of the translation invariant objective function. So the attack methods are very simple, and the implementation is very simple. In this slide, I show some results of black box attack against the defense models on the ImageNet dataset. So here we consider 10 defense models. Among them, 8 defense models are based on some previous defense, which based on some maybe adversarial training and the image denoising, transformation, and some random defenses. These defenses are not very effective to defend against adversarial attacks. And we also consider 2 stronger defense models, which based on adversarial training. So here we generate adversarial examples by different methods, and against 4 normally trained models, including Inception V3, Inception V4, and ResNet, and Inception ResNet V2. So we directly test the adversarial examples against these 10 defense models and calculate the success rate. So in this table, we can see that our method achieved much better attack success rate than the baseline method. And if we look at the last rows, we can see that our method can achieve very high attack success rate against the first 8 defense. The success rate exceeds 18%. And for the last 2 adversarial training-based defenses, because they are inherently robust to adversarial attack, our method cannot get very high attack success rate, but it can also improve the performance over the baselines. And in this figure, I show the black box attack success rate under different perturbation badges. So here we want to show that under different perturbation badges, our method can also improve the attack success rate over the baseline methods. Now I would like to turn back to the original formulation of adversarial attack and provide a more general view of black box attack methods. So our goal here is still how to solve this optimization problem when the gradient is available. So for transfer-based attack, we actually use the gradient of a surrogate white box model to approximate the true gradient of the black box model. So here, if we denote ILF as the white box model, and ILF prime to denote the black box model, to denote the white box model, and LF to denote the black box target model. So even if we do not know the gradient of the black box model, we can use some gradient of the white box model to approximate it. The previous method I introduced mainly adopt better optimizers to utilize the transfer gradient to improve the transferability. So, and on the other hand, score-based attack usually rely on zeroth order optimization techniques to generate adversarial examples. So the popular method in zeroth order optimization literature is the random gradient-free method. So in this method is also, sorry, is there a question? Okay, let's continue. So the random gradient-free method is also very simple. So it's based on it's also based on the finite difference. This method, in this method, we first draw Q random queries UI randomly from maybe a high-dimensional distribution, and we then calculate the loss as the new point x plus sigma UI, and we then subtract the loss as the original input x. The loss difference divided by sigma is actually the directional derivative of the loss function with respect to the random vector UI. We multiply the directional derivative with UI, and the result is a gradient estimation GI hat. Usually we can do this procedure for all sampled vectors UI, and we average the gradient estimation to get the overall gradient estimator G hat. Usually, the random vectors UI are sampled from a distribution on a high-dimensional input space. So here we use the capital letter D to denote the dimension of the input space. And if we assume that the loss function L is differentiable and the parameter sigma approaches 0, we can derive that the gradient estimator GI hat approximates the multiplication of UI transposition and the gradient of the loss function. If we can make the distribution as maybe a uniform distribution on the unit hypersphere in the d-dimensional space, the multiplication of UI and UI transposition equals the identity matrix. In this way, the gradient estimator GI hat approaches the true gradient of the loss function. So for score-based attack, the gradient we can actually make the gradient estimator to be an unbiased estimation of the true gradient. So by taking a general view of gradient estimation, we actually face a bias variance trade-off here. So for transfer-based attack, the transfer gradient cannot be very accurate to estimate the true gradient, such that it has a very high bias. And for score-based attack, although we can get an unbiased gradient estimator, but the input dimension D is usually much higher than the number of queries Q. So the gradient estimator has a very high variance. So in this work, we try to address the bias variance trade-off of gradient estimation, and we aim to develop a better method to estimate the gradient more accurately. So this is a main goal of our work. So this work is published at NERS 2019, and IEEE transactions Permi in the last year. So I will first introduce the gradient estimation framework introduced in our paper. The gradient estimation framework enables us to analyze different gradient estimators and help us find better estimators under the unified framework. So first, suppose that we have a set of gradient estimators, which may be given by different gradient estimation methods, and we want to choose the best one in the set. To be more formal, we need to design a loss function G for each gradient estimator, such that we can measure the performance of different gradient estimators. And if we have such a loss function, we can find the best gradient estimator that achieves the lowest loss value of the loss function. Our work introduced a loss function shown in this form. So it is basically the squared L2 distance between the true gradient and the gradient estimator. But note that here we introduce a scaling factor B here, and we actually want to minimize the distance between the true gradient and the scaled gradient with respect to the scaling factor B. The motivation of doing this is to eliminate the effect of the scaling of the gradient estimator. Recall that we usually normalize the gradient in typical adversarial attack algorithms. So the magnitude of the gradient estimator is not important, but the direction of the gradient estimator is more important to ensure the performance of black box attack. So in the loss function, we need to introduce a scaling factor to make our loss function only focus on the direction of the gradient estimator rather than its magnitude. Based on the gradient estimation framework, we conduct some theoretical analysis of the random gradient free methods. So in this slide, I will introduce the Mean Theorem developed in our paper. So we first assume that the gradient estimator G hat is given by the random gradient free method, and the in the RGF method, we assume that the random vectors UI are sampled from a distribution on the unit hypersphere of the input space. It means that the L2 norm of the random vectors equals to 1. Then we can derive the loss of the gradient estimator when sigma approaches 0, which is shown in this equation. At first glance, the form may be a little bit complicated, but if we look more deeply, we can see that except the number of queries to obtain the gradient estimator, the only term that appears in this equation is a matrix C. C is actually defined as the autocorrelation matrix of the random vector UI. It is calculated as the expectation of UI and the UI transposition. So from this theorem, we can see that if we would like to find a better gradient estimator, we can design a better matrix C to minimize this loss function. And it means that we need to define a better random vector to get the better C. And we need to design a better distribution to sample the random vectors UI. To be more concrete, the random vector UI is a 1 by D vector, and the matrix C is a D by D matrix. Okay. So for the ordinary random gradient free estimator, the random vectors UI are usually sampled from an unbiased distribution, such as a uniform distribution on the unit hypersphere, such that the autocorrelation matrix C equals to equals to the scaled identity matrix. So in this work, we want to develop a better matrix for gradient estimation. And in this paper, we propose two prior-guided random gradient free methods. The basic idea is to integrate the transfer-based attack with the query-based attack method. So our method treats the gradient of a surrogate white box model as a transfer-based query, and we study how to combine the transfer gradient with queries. So our first method is called biased sampling. So from its name, it can be easily understood as sampling the random vector CUI that are biased towards the transfer gradient way, and the balance between the transfer gradient and the random directions is controlled by a hyperparameter lambda. Here we provide a visual illustration of our method. We actually sample the random vectors biased towards the transfer gradient, and we sample the random vectors on the right circle in this figure. So here we provide some conditions that is useful for understanding our method. In the extreme case, if lambda equals to 1 and UI equals to V, this means that we directly use the transfer gradient as the gradient estimator, and we do not use any queries. And on the other hand, if lambda equals to 1D, our method degenerates to the ordinary random gradient free estimator. And this means that we do not use any prior information of the transfer gradient. Although we may use a constant for the hyperparameter lambda, in this paper we try to find the optimal lambda under our theoretical framework. So it is also the main contribution of our paper. So here I would like to introduce some details to solve for the optimal lambda. To do so, we need to introduce another notation alpha. Alpha is defined as the cosine similarity between the transfer gradient V and the true gradient. Intuitively, alpha denotes the usefulness of the prior information V, because if alpha is higher, it means that the transfer gradient approximates the true gradient better. So the usefulness of the prior is much higher. And under our gradient estimation framework, we can derive an analytical form of the optimal lambda star, shown in this equation. So this equation seems to be a little bit complicated, since it is a very complicated form. And we show the curves of the lambda star along with the alpha. From the equation, we can draw some findings. First, by theoretical analysis and this figure, we can easily prove that the lambda star is a monotonically increasing function of alpha. It means that we usually need to use a larger lambda when alpha is larger. It makes sense since we tend to rely on the transfer gradient more if it can approximate the true gradient better. One potential issue here is that we actually do not know the value of alpha, since it is related to the true gradient of the black box model, and we do not know this gradient. So we need to estimate the value of alpha, and I will introduce the estimation algorithm later. Now I would like to introduce our second prior-guided random gradient method, which is based on gradient averaging. So let's look back to the formulation of the random gradient free method, in which the final gradient estimator G hat is averaged over Q random Q estimators. This inspires us to view the transfer gradient V also as an estimate gradient and directly average the transfer gradient with the with other gradient estimators. So we propose a gradient average method, which takes a very simple form. The gradient estimator is defined as the weighted average of the transfer gradient V and the normalized gradient given by the ordinary random gradient free method. And in this form, we also have a balancing hyperparameter mu, which is used to control the control the strength of using the transfer gradient. Similar to the bias sampling method, in which we theoretically calculate the optimal lambda, we can also calculate the optimal mu in the gradient averaging method. So here we introduce a new variable beta to denote the constant similarity between the true gradient and the gradient estimator given by the ordinary random gradient free method. And similar to alpha, beta also denotes the usefulness of the random gradient free estimator. Then we can have a theorem of the loss of the gradient estimator given by the gradient averaging method. So this loss is concerned with the constant similarity alpha and the constant similarity beta. So we would like to minimize this loss function with respect to the hyperparameter mu, and we would like to find the optimal mu that lead to the best loss values. After solving this problem, we found that the optimal mu is given by this form. It is much simpler than the formulation of lambda star. And in this slide, I will show the loss curves of different gradient estimator given different constant similarity between the true gradient and the transfer gradient alpha. And we show 4 curves here, which corresponding to 4 gradient estimators, including the transfer gradient showing the green curve, the gradient estimator given by the random gradient free method, which is showing the blue curve, and the two prior guided random gradient free method showing the yellow and red curves. Since the random gradient free method does not use any prior information of the transfer gradient, so the loss value of the random gradient free estimator is constant. And for our method, the loss value decreases when increasing the constant similarity alpha. From this curve, we can see that our method achieves lower loss than the baseline random gradient free method and the transfer gradient. It means that we can better utilize both the transfer gradient and the query information. And from this figure, we can also see that the gradient averaging method shown in the yellow curve can also obtain better lower loss values than the biased sampling method, which may indicate that the gradient averaging method may be more effective than the biased sampling method. Finally, I would like to introduce our method for estimating the constant similarity alpha. Recall that alpha is defined as the constant similarity between the true gradient V and the true gradient and the transfer gradient V. So we can see that the numerator corresponding to the multiplication of the true gradient and the transfer gradient can be easily estimated by the finite gradient free by the final difference method. So the key problem here is to estimate the norm of the true gradient. Since the norm of the true gradient is a scalar, it is much easier to estimate than the direction of the true gradient, which is a very high dimensional vector. So I will not introduce all the details of estimating the norm of the gradient, and our basic idea is to introduce as variable homogeneous function, and we can simply derive the unbiased estimator of the gradient norm. In our work, we choose a very simple function for the homogeneous function, and the norm can be simply estimated by S queries given in this form. And in our experiment, we found that using about 10 queries is sufficient to obtain an accurate estimation of the gradient norm. So I would like to show some results of our gradient estimation. First, in this figure, I show some gradient estimation accuracy. In the left column, I show the constant similarity between the estimated gradient and the true gradient. The blue curve corresponds to using a constant lambda to obtain the lambda or mu to obtain the estimated gradient, and the red line refers to using the optimal lambda to calculate the constant similarity. It can be seen that using the adaptive optimal hyperparameter in different methods can give a more accurate, can give a higher constant similarity between the estimated gradient and the true gradient. So it means that using the optimal hyperparameter derived by our theoretical framework is better than using maybe a predefined hyperparameter. And in the middle column and the red column of this figure, we show the change of the hyperparameter and the constant similarity between the true gradient and the estimated gradient along with the attack iterations. It can be seen that when the attack proceeds, the constant similarity between the transfer gradient and the true gradient becomes lower. But our method can also use this information to obtain a more accurate gradient estimation. In this table, I show some results of attacking some ImageNet classifiers. We consider 3 models, including the Inception, V3, VGG, 16, and ResNet, and we show the attack success rate as the average number of queries and the median number of queries required to generate a successful adversarial examples. So compared with the baseline method, we can see that using our method can achieve both high attack success rate and high efficiency. It means that we need fewer queries to generate a successful adversarial examples. Our method can also be extended to using multiple surrogate models to get the transfer gradient. In transfer-based attack, the typical method is to use an ensemble of white box models to improve the transferability of adversarial examples. So here, suppose that we have M surrogate white box models, and they gives M gradient directions to use in our pre-guided random gradient free method. So a naive method that can equally average this gradient to define the transfer gradient. And in our paper, we actually develop a better method which is based on subspace projection. So the main idea is to view the gradient of the M surrogate model as a M-dimensional subspace, and the best approximation of the tree gradient that lies in the subspace is the projection of the gradient onto the space. So the projection of the true gradient onto the subspace can be found by this method. Here is the formulation. It involves the multiplication of the true gradient and the transfer gradient of different models, and the multiplication can be easily estimated by the finite difference method. Here we also compare the results of using multiple white box models to improve the black box attack. And we show that by using maybe 3 models, including RaceNet inception and the inception RaceNet, we can have very high efficiency of attacking these black box models. We need about less than 100 queries to issue a successful attack. So the previous work is mainly concerned about the theoretical framework to find a better attack method. And I will introduce our other works that is mainly based mainly developed based on practice. So the most practical method to find better adversarial attack is to automatically discover adversarial attack algorithms that can perform well than maybe human designed algorithms. So the AutoML field is also a very hot research field, which mainly aim to automatically find better machine learning algorithms to solve some specific tasks than human designed ones. So we use similar ideas from AutoML to design adversarial attacks automatically. So our motivation is as follows. Usually we need to design adaptive attacks to evaluate the defense models. So it is very labor expensive and require a lot of human experts to design such an adaptive attack. And we think that automatically discover adversarial attack can also serve as a reasonable baseline to measure the strength of our design attacks and expand the rationality of the assumptions made in these attacks. So in this work, we focus on the decision-based black box attacks, mainly due to 2 reasons. The first one is that the existing decision-based attacks are quite heuristic, since these methods are developed by humans with very heuristic search methods. And the existing decision-based attack usually have unsatisfactory performance. So in this work, we propose an automatic decision-based attack. We mainly rely on the random walk framework, which is a basic framework for decision-based attack. So the main idea of random walk-based attack is to do random search on the decision boundary of the black box model and move the solution close to the original example while maintaining the adversarial ability. So we first define an algorithm template for the random walk framework. So in each iteration, we usually random generate a new solution X prime, and we test whether X prime is adversarial and whether the distance between X prime and the original image becomes smaller. And if these conditions are satisfied, we move the adversarial example to the new candidate and we update some information for future search. So using this template, we can use AutoML to automatically find some algorithms in this template, and mainly the generate function, which generates the new candidate for the next search. So in our automatic search, we first need to define the search space, and inspired by the recent work called AutoML0, we also define the search space as basic mathematical operations, including addition, subtraction, multiplication, division, and others. And we use this simple search space to find the adversarial attack algorithms. And there is also another perspective for automatic search is the search method. And in our work, we simply use the random search method, and we use some useful techniques to improve the efficiency of random search, including we need to make the discovered program to be more compact. We use some predefined operations, and we do some input check and the distance check to fill out some poor programs without using the input information and without reducing the distance. So here are two programs discovered by our method, and it mainly consists of some basic mathematical operations to do the adversarial attack method. And we can see that the programs are very short. It means that our discovered programs are very simple. Here we show some results of our discovered algorithms compared with some baseline method, including the boundary and some more advanced method. It can be seen that our methods are more query efficient than the baseline method when using a very small number of model queries. For example, by using 2,000 queries, our method can achieve much higher attack success rate than the baseline methods. So that's all my presentation, and I would like to thank my collaborators, including my PhD advisor Junju and some other students and professors in our group. Okay, that's all. I would like to answer some questions.
Thank you very much for your great talk. I have a general question. What do you have done quite a lot of works on adversarial attacks in black box, white box ways. What do you think of the future of the attacks? You know the security evaluations in this related field. Yeah.
Yes, it's a good question. From my perspective, I would like to focus more on physical adversarial attacks, since the work I introduced are mainly based on digital adversarial examples, which means that the adversarial examples are crafted for computer stored images and other forms. But we need to make these adversarial examples realizable in the real world. For real world attacks, the adversarial examples may be destroyed by maybe by the loss of printers and maybe some image transformation. So we need to craft physical adversarial attacks with high robustness. And another direction is that we maybe need to consider physical attacks against black box systems. So it can really raise real security concerns.
I see. So sometimes in terms of the physical attacks, my concern sometimes is we do not have a mathematical tools, for example, the norm to describe the differences between the physical adversarial data and the natural data. So
yes.
Yes. What do you think about this? Yeah.
Yes, it's a good question. For physical adversarial attack, we usually use the LP norm is maybe not sufficient for measuring the physical adversarial examples. So I see that maybe they usually use L0 norm to measure the perceptibility of physical adversarial examples, mainly in the form of adversarial patches and other forms. So it's a good question, and we maybe develop better threat models.
I see. All right. Thank you very much. If there are no questions, other questions coming up, let's thanks again for Dr. Dong to come here to give us his wonderful talks on his wonderful research. Hopefully in the future, you could visit us in Tokyo physically in our Nihonbashi office. Thank you.
Thank you.
Again.
Bye.
Bye-bye.
Bye.
All right. Suravanti, are you there? Great.
Yes.
Hi, Suravanti. Firstly, I'm going to introduce you to our audience. Then you're going to proceed to your talk. Great. Suravanti Adebali is a PhD student at the Indian Institute of Science, Bangalore. She is pursuing research in the area of adversarial robustness of deep networks at the video analytics labs in the Department of Computational and Data Science. Prior to this, she worked for 10 years at SanDisk, now Western Digital, in analog and digital circuit design. Suravanti is interested in exploring the vulnerability of deep networks and building algorithms to improve their robustness. She is a recipient of the prestigious Google PhD Fellowship, Prime Minister Fellowship for Doctoral Research, and Qualcomm Innovation Fellowship. She today going to give us her talk about the toward efficient and effective adversarial training. Hi, Suravanti, please go ahead.
Hi, thank you. Hello, everyone. I'm Sravanti. I'm a PhD student at the Department of Computational and Data Sciences at the Indian Institute of Science, Bangalore. Today, I'll be presenting some of my our works on achieving efficient and effective adversarial training. First, I'd like to thank the organizers of the TrustML seminar series for giving me an opportunity to present my work here. Before starting, I'd like to thank my collaborators, and the work which I'll be presenting was done in collaboration with Gaurang, Arya, and Vivek, and also my advisor, Professor Venkatesh Babu. So here is a brief agenda of my talk. First, I'll introduce the area of adversarial attacks and robustness, and then I'll be talking about 3 of my works. The first one aims to achieve adversarial robustness without the use of adversarial samples during training. And the other 2 aim to achieve robustness using single-step adversarial training. And also the last one aims to use a nuclear norm-based regularizer for improving the efficiency and effectiveness of adversarial training. So deep neural networks are being widely used in many applications of computer vision and other areas as well. Although they achieve near human performance on many benchmark data sets, they're still not as robust as the human visual system. Deep networks are known to be vulnerable to carefully crafted imperceptible attacks known as adversarial attacks. So here we can see an example that the image on the left is a natural image and it's being predicted correctly as a hamster with very high confidence. But when we add this imperceptible noise to it, although the image on the right looks very similar to the natural image, the deep network predicts it as a banjo, which is a completely unrelated class with a very high confidence. So these attacks could have disastrous implications in many critical applications. For example, we can see here that hackers could trick a Tesla into accelerating by 50 miles per hour by just attaching a 2-inch piece of tape on the speed limit board. And face recognition systems could be tricked into predicting a different person by just wearing a specially designed pair of spectacles. And here we see that a benign mole is being recognized as malignant by just rotating the image by a certain amount. So the compelling need of securing these systems has propelled the research in the area of adversarial defenses. Some of the early adversarial defenses tried to use input pre-processing based methods to defend against adversarial examples. For example, some non-differential pre-processing steps were introduced on the image before passing it to the deep network. Some examples are bit depth reduction and JPEG compression. So this was actually used to prevent the generation of strong gradient-based attacks, but it was not actually making the model robust. So although these were coming with the advantage of limited or no additional computational cost during training, they were shown to be not truly robust against strong attacks, and these defenses were broken later using the backward pass differentiable approximation and expectation over transformation attacks. The successful defenses involved adversarial training, which I'll be discussing in a little more detail now. So in adversarial training, we first pass the clean images to the network. And like here, I'll be discussing the example of PGD adversarial training, where we consider the cross entropy loss on the clean example. And we maximize this cross entropy loss to generate adversarial examples within a defined threat model. For example, the most commonly used threat models are the LP norm based threat models. So the value of the P in the LP norm and also the radius within which we constrain the examples, they define the threat model. So this way the adversarial examples are constructed, and then we train the network to minimize the cross entropy loss on these adversarial examples for training. So the main aspect which makes this adversarial training computationally expensive is the generation of adversarial examples. And this is typically, this optimization step is typically done by using several steps of optimization, and 10 attack steps are usually used. So based on the number of steps that is used for attack generation, these adversarial training methods can be classified as either single step defenses or multi-step defenses. So multi-step defenses are, they achieve state-of-the-art robustness today. And like two of the very popular methods which achieve state-of-the-art results are the PGD adversarial training and the trades. So the only concern with these methods is the high computational cost. Because these methods use around 10 steps of optimization for attack generation, which makes it 11 times costlier in terms of computation. So there have been attempts of using single-step attacks, single-step gradients for attack generation. And the advantage of this is the lower computational cost. But these methods are susceptible to gradient masking, which leads to a false sense of security. So as we can see here, here we show the loss surface of a model, which is plotted against the gradient direction at a given data sample. So we consider the data sample to be at 0, 0. And another direction is a random direction orthogonal to the gradient direction. So as we can see here, when we do FGSM adversarial training or single-step adversarial training, the loss surface becomes very complex. And this prevents the generation of strong single-step attacks during the course of training. So because of this, the model is not truly robust, but there is a false sense of robustness towards single-step attacks. Whereas when we do multi-step adversarial training, such as PGD, it actually leads to a local smoothness around the data sample, which is what we need in, which is the aim of these adversarial defenses. So these single-step defenses, they tend to be more unstable for specifically for longer training schedules and for larger model capacities. So we now talk about one of our works on achieving adversarial robustness without the use of adversarial samples during training, which was published at CVPR 2020. Here I give the links of our paper and our code as well. So we'll discuss some preliminaries before going ahead. So an image is composed of several bit planes. So it can be considered as a weighted sum of different bit planes of the image, which are weighted according to their relative importance. For example, the bit plane 7 for an 8-bit representation of an image, it consists of the MSBs of the image, and the bit plane 0 consists of LSBs. As we can see here, the MSBs contain most of the information. So at least for a data set such as CFAR 10, probably some of the MSBs are sufficient to get a very high accuracy. But we see that L-infinity norm-bound perturbations, which actually reside in the LSBs, are able to in fact cause misclassification with a very high confidence. So so we try to enforce consistent feature representations between the image and a quantized version of the image, so that the network learns to give more importance to the coarse features which are present in the MSBs. So in this work, we introduced this bit plane feature consistency regularizer, which tries to enforce an L2 norm regularizer between the pre-softmax values of the clean image and the pre-softmax values of the quantized image. So the overall loss that we use in this method is basically the cross entropy loss on clean samples. This basically ensures that the network is able to use the information from all the bit planes for classification. For example, in a data set such as ImageNet, it might actually be very important to even look at the finer details. And the second term ensures that there is the representations of the full image, which consists of the coarse and fine features, and the quantized image, which actually consists only of the coarse features. These representations are consistent, and we weight this using a factor lambda. We increase this lambda over the training epoch, because initially the network is smooth and we don't need a higher weight of this smoothness regularizer. And we notice that as we increase the as we change this lambda, the rate of increase in lambda, we see this robustness accuracy trade-off. And we basically select the lambda at which we obtain clean accuracy, which is similar to the PGD baseline. So we, since this method does not involve the use of adversarial attacks for training, it is important to evaluate it against a range of attacks to ensure that the robustness that we see is not because of gradient masking. So we evaluate it against several data sets and also different kinds of attacks. We also evaluate against adaptive attacks and gradient-free attacks to ensure there is no gradient masking. I'll be presenting some of these results here. So here we show the results across 3 data sets, and we compare against adversarial training methods such as single-step methods and also the 10-step method, and also some of the methods which like normal training and mix-up, which do not use adversarial samples for training. So as we can see here, without the use of adversarial samples for training, the model is never robust against strong attacks such as PGD. Whereas the proposed method, in spite of not using adversarial samples during training, we achieve a significant amount of robustness, which is although less than the multi-step training methods, it is a significant boost over the methods which do not use adversarial samples for training. We also show that this method can scale to ImageNet, and the trend in robustness when compared to the PGD adversarial training is similar between CFAR10 and ImageNet. So this demonstrates the scalability of the proposed approach to large-scale datasets. So the main advantage is the computational complexity, which is similar to the normal training regime, and it's much lesser than the multi-step training regime. In addition to the computational complexity, another advantage of this method is that it can extend to more complex threat models as well. For example, it can be used for defending against real-world adversarial attacks. So the real-world adversarial attacks are usually sparse attacks because they are easier to implement. For example, the patch attacks and L0 norm-bound attacks. So the problem with adversarial training on these threat models is that the attack generation is harder, and also it can be more computationally expensive. Like it might require around 10 to 50 attack steps, since there is no real constraint on the amount by which each pixel is perturbed. So this makes standard adversarial training much more expensive. And another constraint in the real world is that the attack needn't be restricted to a single threat model. So generalization to unseen attacks is very important. So in one of the recent works, we show that this framework of BPFC can be extended to other threat models as well. So here we show the patch threat model. In this, we pass 3 images to the network. So one is the natural image. One is an image where we place a random patch at a random location, and another is XIB, which is a cutout-based augmentation, where we simply blank out the portion where this patch is placed. So similar to the work that we saw earlier, we enforce consistent feature representations between xib and xi tilde, along with the minimization of cross entropy loss. So here we consider a convex combination of cross entropy loss on xi as well as xib, and we have the squared L2 norm regularizer between the pre-softmax values of xib and xi tilde. So we show that the proposed method, which is basically placing the patch at a random location and a random patch, so it is basically able to achieve robustness, which is similar to the standard adversarial training methods for patch-based attacks. So in addition to this, we also observe that if we use a single gradient step for location optimization and also for attack optimization, we achieve a significant boost over the multi-step adversarial training methods as well. So we achieve this at a much lower computational cost. We also observe that this method leads to much better generalization to unseen attacks. For example, here we train the model using square 5x5 patch attacks, and we evaluate it against patch attacks of different shapes and also against other threat models such as L1 and L0 norm. And we note that the average accuracy against unseen threat models is significantly higher using the proposed approach, and the computational budget is also much lesser. We next move to our work on achieving adversarial robustness using single-step adversarial training. So this was the title of this work is Guided Adversarial Attack for Evaluating and Enhancing Adversarial Defenses, and it was published at NeurIPS 2020. So we see that there's a close, strong attacks and robust defenses are very closely coupled. So strong attacks are basically needed for reliable evaluation of robust defenses, and it also leads to the development of better defenses since they are evaluated well. And we need strong attacks also for better adversarial training, because adversarial training uses attacks in the algorithm. And we also see that robust defenses motivate the generation of stronger attacks. For example, some of the defense-specific attacks could work very well for other defenses as well. So there's this attacks and defenses are very closely coupled to each other. And in this work, we look at the development of a strong attack, which is called gamma, and we see that this attack can be used for generation of better single-step defenses as well. Here we visualize the loss surface of around a data sample, which is assumed to be at the center of this circle. So this is a schematic diagram of the loss. And we consider this dotted circle as the threat model. So here we show three classes, C1, C2, and C3. C1 is the class to which the clean sample belongs. And the goal is to find an adversarial example which is within this threat model. So using standard untargeted attacks, because since the loss surface around this data sample is non-convex, it is possible that we don't find the adversarial example within the threat model, although it exists, as shown in this figure. So this is usually mitigated by either using multiple random restarts of the untargeted loss or by using multiple targeted attacks. So as we can see here, if we use a targeted attack against C3, we'll be able to find the adversarial example. However, this comes with an additional computational cost. In this work, we aim to introduce an L2 squared L2 relaxation term so that we can utilize the softmax vector of the clean image for a better initial optimization. So basically, this additional relaxation term, in addition to the true max margin objective, which is used for misclassification, this smooths the loss surface around the data sample and makes this initial direction much more reliable. And we decay this L2 relaxation term to 0 over the training epoch. so that the remaining iterations of the attack, they're actually able to maximize the true max margin objective, which leads to misclassification. Here we visualize the loss of its plots of an FGSM model, which is basically generated using single-step adversarial training. As we can see, the loss surface of the cross entropy loss, there is some gradient masking at the data sample, which prevents the generation of strong attacks. And the same amount of gradient masking is also there when we try to maximize the max margin loss. However, when we introduce the L2 relaxation term that we discussed in the previous slide, it actually reduces the gradient masking at the data sample, and it enhances the strength of the single step attack. So basically, using a single gradient step, we can reach, we can maximize the loss within the threat model effectively. So using this proposed attack, we show that we are able to generate a much stronger attack against several defenses which are taken from the robust bench leaderboard. So we compare our method against the standard PGT attack and also some of the attacks which are there in the auto attack framework. We also introduce another variant of the attack, which is based on Frank-Wolf optimization. And the proposed attacks are much stronger on several defenses. And we also verify this for 5 random restarts of the attack. And even in this setting, it outperforms the existing attacks. We also show that in a multi-targeted framework, where we utilize a targeted loss function for the top 5 targets, even in this framework, the proposed attack outperforms the existing attacks. We now use the proposed attack for single-step adversarial training. We call this defense as guided adversarial training, or GAT. So here I'll be presenting the algorithm of GAT. First, we add this random Bernoulli noise of magnitude alpha to every pixel in the image. And the loss that we maximize for the generation of attack is a combination of cross entropy loss and the L2 regularizer, the squared L2 regularizer between the softmax values of the adversarial image and the clean image, as we have seen earlier. These two are weighted with a factor lambda. So we maximize this loss and we constrain the attack to be within the threat model. And for adversarial training, we again use the same loss function, which is a combination of cross entropy loss on clean samples and the squared L2 regularizer between the softmax values of the perturbed image and the clean image. It is again weighted by the same factor lambda, which was used for attack generation. And this is repeated for several training iterations. So using this proposed regularizer for single-step adversarial training, we show the results on CFAR 10 for both ResNet 18 and wide ResNet architectures. So the proposed method GAT on ResNet 18, it outperforms several single-step defenses and also achieves robustness, which is similar to PGD and trades, which are multi-step defenses. And on the wide ResNet architecture as well, we obtain significant boost over the single-step training method. Fast is better than free because FBF has a certain amount of gradient masking at higher model capacities. And we also obtain results which are similar to the multi-step training methods. Here we visualize the loss surface plot of several defenses. And as we can see, FGSM adversarial training has a certain amount of gradient masking, whereas the proposed method, it achieves a loss surface which is similar to the multi-step training methods. We next move to the third method, which is to use nuclear norm-based regularizer for generation of single-step defenses. So the title of this work is Towards Efficient and Effective Adversarial Training, and recently it has been published at NeurIPS 2021. So we first introduce some preliminaries on the nuclear norm of a matrix. So we represent the nuclear norm using the norm star of A. And it is defined as the sum of the singular values of the matrix, which is also equivalent to the trace of the matrix square root of A star A, where A star is the Hermitian conjugate of A. So the nuclear norm of a matrix forms a uniform upper bound of the Frobenius norm, and we show that here. And it also forms a tight convex relaxation of a rank of a matrix. So it can be used as a differentiable surrogate for optimization instead of the rank of a matrix. So here we show how nuclear norm regularizer can be used for adversarial training. So we take a matrix X, which is composed of the various images x1 to xm arranged row-wise. And we consider x plus delta or x tilde as the matrix composed of adversarial examples. So the pre-softmax values of x are denoted by f theta of x, and the pre-softmax values of the adversarial image are denoted by f theta of x plus delta. So in this, the loss that we use is a combination of cross entropy loss on the clean samples, as well as the nuclear norm regularizer between the difference of pre-softmax values between the of the clean image and the perturbed image, which is f theta of x tilde minus f theta of x. So different from existing methods of adversarial training, this method actually utilizes the batch statistics for training. So different images in a batch are able to guide the optimization of each other in adversarial training because of the nuclear norm based formulation for training. So here we compare the nuclear norm of robust and non-robust samples across various attacks and defenses. So on the x-axis, we have different defenses and attacks. And on the y-axis, we show the nuclear norm. So we separately compute the nuclear norm of robust and non-robust samples. And we notice that the nuclear norm of robust samples is always lesser than the nuclear norm of non-robust samples. And this justifies the use of the nuclear norm-based regularization for adversarial training. We now look at how we generate a nuclear norm-based attack. So we consider a training mini-batch B of M samples. And as we have seen earlier, X is composed of the images x1 to xm in a batch, and Y is the labels y1 to ym. So delta is the perturbation delta 1 to delta m, and we initialize delta with Bernoulli noise of magnitude alpha. So we maximize the sum of cross entropy loss on adversarial samples and the nuclear norm regularizer between the perturbed image and the clean image. And finally, we clamp the generated attack to the perturbation bounds epsilon and the image limits 0 and 1. So we find that when we actually maximize the nuclear norm of difference between predictions of the adversarial image and the clean image, it maximizes the singular values of the matrix, and it results in a much more diverse attacks across the batch, rather than the standard cross entropy based loss, which actually leads the attack to go to the most confused class. So here we show the confusion matrices of nuclear norm based attack and Frobenius norm based attack. So this is plotted for a normally trained model on the ResNet 18 architecture for CFAR 10 dataset. And we notice that when we do a nuclear norm based attack, the target classes are much more diverse than a Frobenius norm based attack. And also, if we notice the diagonal entries of the matrix, then we can see that the nuclear norm based attack is stronger than the Frobenius norm based attack as well. We now present the algorithm for nuclear norm based adversarial training. So the this is for the single step nuclear norm based attack. We consider the cross entropy loss on the adversarial samples and the nuclear norm regularizer, and this is maximized for the generation of attack. For adversarial training, we again use the same loss function and the same regularizer lambda. we increase the value of lambda over the training epoch. And we repeat this for several training iterations. We introduce another variant of this nuclear norm attack by using model weight averaging. So here it has been shown that weight averaging leads to a wider optima and hence better robustness on the test set. So better generalization to the test set. So after every training iteration, we do exponential weight averaging of the model. We also introduce a two-step variant of the nuclear norm-based defense, where in the first attack step, as we have seen earlier, we use a combination of the cross-entropy loss and the nuclear norm-based regularizer, whereas in the second attack step, we use only the cross-entropy-based loss. So the first attack step basically results in a more reliable gradient direction because of the presence of the smoothing term, and the second attack step results in a more stronger optimization because cross entropy loss leads to a better misclassification. In another variant of the nuclear norm based defense, we introduced weight averaging along with the two-step defense. So here we generate the first attack step from the EMA model so that it generates a much more reliable gradient. And in the second attack step, we use the cross entropy loss from the model which is being trained. So again, here the first attack step results in a more reliable gradient direction, and the second attack step is stronger for the generation of a stronger attack. Finally, we introduce this hybrid adversarial training, which tries to bridge the gap between the single step and the two-step defenses which were introduced earlier. So here we track the cross entropy loss on clean samples across training epochs. And we notice that when we do single step adversarial training for either longer training epochs or on larger model capacity, it has been observed in prior work as well that it leads to gradient masking. So we track the cross entropy loss on clean samples over training iterations to identify at the point of time at which gradient masking starts, and we switch to the two-step defense at that time. So this is motivated by prior work which has been cited here. So as we can see here, when the training goes on smoothly, the loss surface at this point is smooth and it is as expected. But suddenly at this point, we see a large drop in the cross entropy loss on clean samples. And if we look at the loss surface at this point, then it suddenly becomes more convoluted and prevents the generation of stronger single step attacks. So in order to identify this, we basically track the cross entropy loss on clean accuracy across epochs. And we detect this point where there's a sharp drop in the cross entropy loss, and we switch to a two-step attack at this point. And we switch back to the single step attack when the loss recovers. So unlike the prior works, we don't use a separate validation set for this, and we just track the clean accuracy on the trained samples. And the switching between the single step and two-step attack is also done quite smoothly. So just with an additional computational budget of around 5 to 6 training epochs, we actually obtained results close to the two-step defense within the computational budget of a single-step defense. So here we show some of the results on CIFAR 10 dataset for a ResNet 18 architecture. As we can see, the proposed method NuAT, we are able to achieve better results when compared to the existing single-step training methods, and it also achieves better robust accuracy when compared to PGD adversarial training and trades. And when we combine NuAT with weight averaging, we in fact achieve a significant boost over the prior methods with weight averaging and also trades with weight averaging. We also achieve comparable performance when compared to the AWP defense, although we are still lesser than that. And on the so we show that this the nuclear norm defense can work well even on larger model capacities such as wide ResNet. So using the base defense NuAT, which is a single step defense, we achieve better results when compared to GAT and FBF at significantly lesser number of training epochs. And using the two-step variant of the defense, we get a boost with respect to the multi-step methods such as trades and PGD as well. Finally, we combine the advantages of the single-step defense and the two-step defenses in using the hybrid training method. And using this, we are able to achieve a robustness which is similar to trades and PGD. We show that the method performs well across different data sets as well, CFAR10, ImageNet 100, and MNIST. And also we show some experiments on the full ImageNet data set in the paper. Here we show the computational time versus robust accuracy across various defenses, which include both single-step and multi-step defenses. So here, the variants of the proposed defense are shown here. And the FBF defense is computationally much cheaper, but the robust accuracy is also lesser. So we see that the single step and hybrid variants of the proposed defense, they achieve a significant boost in adversarial robustness at a very low computational time. And the two-step variant, the two-step variant of this nuclear norm defense, it is able to achieve a boost over trades and PGD-AT as well at a much lower computational cost. So to summarize, we have seen 3 works. The first one talks about achieving adversarial robustness without the use of adversarial samples during training. Here, the computational budget is comparable to standard training, and we've seen that it also extends to other threat models where gradient-based attacks are harder. Next, we saw how we can achieve adversarial robustness using single-step adversarial attacks. In this work, we first present an attack, gamma or guided adversarial margin attack, which achieves state-of-the-art robustness against various defenses and when compared to existing attacks. And we use this attack in single-step adversarial training in a defense which is called guided adversarial training, which outperforms existing single-step training methods and also achieves robustness comparable to the multi-step training methods. And finally, we use the nuclear norm-based regularizer to achieve more efficient and effective adversarial training. We have seen the single-step and two-step variants of the defense. And finally, we talk about the hybrid adversarial training, which combines the advantage of the single-step and two-step defenses. So I'd like to thank once again the organizers of this TrustML series for giving me an opportunity to present my work here. And I also thank the funding agencies who supported our work. I'll be happy to take questions.
Thank you very much for your great talk. Basically, I have a questions. I already typed it in the chat box. Why the NuAT cannot boost the robustness of multi-step adversarial training method?
Yeah, that's a great question. So basically, we use the nuclear norm regularizer. So there are 2 uses of this. So one is to impose the local smoothness, which is more important in single-step adversarial training methods, because we need to be able to optimize the loss effectively within a single step, which means the first attack step needs to be very reliable, and the nuclear norm-based regularizer helps with that. And secondly, it leads to more diversification of the attack. So the diversification of attack can actually definitely help in multi-step adversarial training methods as well. And surely this can be tried out.
Okay, thank you. I also have a quite general question. What do you think of the future perspective of adversarial training? What do you think about this?
Yeah, so in future, like so far, we have mainly been focusing on L infinity and L2 threat models for adversarial training. So, but when we look at the real world, we actually need to consider more perceptual threat models. So in future, it would be good to actually formalize the evaluation against these perceptual threat models and also construct defenses and maybe efficient defenses against these perceptual threat models. And also we see that we can actually achieve a very good boost when we use additional training data. But can we actually use better data augmentation methods to achieve such gains in robustness without the use of extra data or GAN-based methods?
I see. Thank you very much. If there are no other questions coming up, let's thanks again for our valuable guest, Surmati, to give her wonderful talks on her research. Hopefully, in the future, you could visit us physically in our Nihonbashi office in Tokyo, and we also welcome the group members in Professor Babu's team to come to visit us. Thank you very much. Bye-bye. All right, this is the end of our today's seminar. Thank you for your attendance.